All right. I appreciate everyone's patience. I was getting phone calls since 6:30 a.m., so appreciate it. Not on this, don't worry. All right. Good morning. How is everyone? Okay, got sleep? Welcome to the witnesses. Welcome back for two of them. All right, as a reminder, I'm Jennifer Homendy, and I'm chairwoman of the National Transportation Safety Board. This is day 2 of our investigative hearing on the fatal accident involving UPS Flight 2976, which crashed during takeoff from Louisville Muhammad Ali International Airport in Louisville, Kentucky on November 4th, 2025. Yesterday's proceedings, which are available on NTSB's YouTube page, focused on fleet safety processes. I'm joined once again by my fellow board members, Vice Chairman Michael Graham, Member Tom Chapman, and Member John DeLue, who likes to work the crowd every morning. I'm just joking with you.
That's okay. I'll take it as a compliment.
It is a compliment. Together, we comprise the Board of Inquiry for this investigative hearing, the notice for which was published in the Federal Register on May 4th, 2026. Behind me is Mr. Eric Johnson, who will provide legal support, and Mr. Chi-Hoon Shin. Please start us off with the safety briefing and staff introductions. And Mr. Shin is our investigator in charge and our hearing officer.
Thank you. Please silence your electronic devices if you have not already done so. Restrooms are in the lobby to the left when you exit the boardroom. We will now share important safety information for those here in person. Please play the video.
Hello, and welcome to the NTSB boardroom. Before we get started with today's meeting, I'd like to quickly walk you through our emergency procedures. First things first, please take a moment to silence your phones or other electronic devices. If you need the restrooms, they're just outside the boardroom on the left side of the lobby. If someone experiences a medical emergency, our on-site Federal Protective Service officers are trained to respond. They'll call 911, perform CPR if needed, and use the automated external defibrillator device mounted in the lobby between the boardroom exit doors. They're also trained to provide first aid. There's a first aid kit at the security desk in the lobby. If we're asked to shelter in place, like during severe weather or a security incident, please stay seated and listen for instructions. Our security team will manage the situation and let us know when it's safe to leave. If the fire alarm sounds, please follow NTSB staff to the nearest exit. There are 2 main options. You can exit via the stairs next to the stage, or you can exit the same way you came in through the lobby. Please walk, don't run. Once outside, you'll be directed to an assembly area. Stay there until we're clear to come back inside. If there's a small fire, our security officers are trained to respond using one of the fire extinguishers. You'll find them in 3 locations: by the stairwells on either side of the stage at the front of the boardroom, mounted on the wall at the back of the boardroom, and near the security area in the lobby. For anyone who needs an accessible evacuation route, you can use the door on the left side of the lobby, which leads you into the parking garage. From there, turn right and follow the walkway to the street level. NTSB staff will be available to assist anyone who needs help. And finally, safety is everyone's responsibility. If you see anything that seems off or concerning, please let a staff member or security officer know right away. Thank you for helping us maintain a safe and secure space.
I'd like to now introduce my NTSB colleagues. In the front row, we have the staff who are serving on Technical Panel 2. To my right, Mr. Clinton Crickshanks, Aerospace Engineer for Structures, Mrs. Eloisa Oki, Aerospace Engineer for Structures, Mr. Caleb Wagner, Aerospace Engineer for Aircraft Systems, and Mr. Sunchet Salji, Aircraft Systems Investigator. Behind me in the second row, we have Mr. Errol Jordheim, Structures Engineer, who will operate the audio visuals, Ms. Tatum Butler, Recorder Specialist, who will operate the timer, Mr. Tim LeBaron, Director of the Office of Aviation Safety, and Mr. Akbar Sultan, Director of the Office of Research and Engineering. Chairwoman Hamidi, this concludes my remarks.
Thank you very much, Mr. Shin. And I'd like to begin by once again addressing the families who lost loved ones in this terrible tragedy, and also those who survived but are injured. Please accept our heartfelt condolences, and please know that this is why we do this, is that so that your loved ones are certainly remembered, and we are never want another family to suffer the same pain that you all are suffering today. So with that, I want to remind everyone, and this is not just for families and survivors and others in the audience that were part of this tragedy, but for anybody here. We have members of our Transportation Disaster Assistance Team, our Family Assistance Team, who are here to help connect you with support resources. Can our TDA colleagues please stand? So right here, and then Sarah in the back. So if you need anything, please don't hesitate to reach out to them, and then at any time during this hearing. And also I want to thank the American Red Cross once again. Volunteer mental health clinicians from the Red Cross will be available throughout the hearing. Please do not hesitate to, again, reach out to TDA or reach out directly to the American Red Cross team. And again, we thank them for all their support. All right, moving on to the introduction of the parties. As I call the name of each party to the hearing, I ask the designated spokesperson to please identify themselves and then introduce others at their table. We're going to start alphabetically with Boeing.
Good morning. Thank you, Chairwoman Hamidi. I'm Stella Widener, the Director for Product Safety and Investigations, and today I have with me across the table Eric East, Senior Air Safety Investigator and Technical Fellow. To his left, Nathan Williams, Air Safety Investigator. Kelly Kleemeyer, Vice President and Chief Engineer, Propulsion and Fuels. At the end, Kristen Oslander, Out of Production Chief Engineer. And to my right, Craig Gabriel, Chief Counsel, Quality and Regulatory Matters. Thank you.
Thank you, Ms. Widener. Federal Aviation Administration.
Good morning. My name is Matt Kabeck. I'm the Deputy Executive Director for the Accident and Investigation Prevention Office. With me, I have Heidi Kemner, investigator and member of the Accident Investigation Branch, Deep Gorov from the Aircraft Certification Service, James Wilborn from Aircraft Certification Service, Rebecca Light from Office of Chief Counsel, and Andy Olvis from the Accident Investigation Branch.
Thank you, Mr. Kabeck. International Brotherhood of Teamsters Airline Division.
Good morning, Chairwoman Hamidi and fellow board members. I'm Chuck Landis, Teamsters Local 2727 Emergency Response Coordinator and UPS Lead Service Technician. Across the table, I have Mr. Randy Barrett, Teamsters Local 2727 Power Plant Group Investigator and UPS Aircraft Maintenance Technician. To his, sitting next to him, I have Josh McInerney, Legal Counsel. At the end of the table, I have Mr. Doug Davis, Teamsters Local 2727 Vice President and UPS Aircraft Maintenance Controller. At the end of the table, I have Jim Cocking, Teamsters Local 27 Structures Group Investigator and UPS Aircraft Maintenance Technician. To my right, Mr. Brian Metzmeyer, Teamsters Local 2727 Systems Group Investigator and UPS Aircraft Maintenance Technician.
Thank you so much, Mr. Landis. ST Engineering, San Antonio Aerospace.
Good morning, Chairwoman Hamidi and board members. My name is Chris Sentz. I am the Vice President of MRO Operations at STAE San Antonio. To my right is David Harrington. He's our legal counsel. To his right is Daniel Perez, our SMS manager. Across the table from him is Henry Gallegos, our Director of Engineering. And across the table from me is Yip Hin Ming. He is our Executive Vice President of STE Executive.
Thank you very much, Mr. Hentz. And United Parcel Service, or UPS.
Good morning, Madam Chair and members of the board. I'm Captain David Smith, Vice President of Airline Safety. With me today, sitting across from me and moving clockwise around the table, Ms. Shannon Harris, Manager, Safety Management Systems, Captain Jacob Chambers, Flight Safety Investigator and Investigation Party Coordinator, Mr. David Gladson, Aircraft Engineer, Structures, Mr. Chad Nattinger, Aircraft Engineer, Systems, Mr. Mark Dumbroff, Legal Counsel. Thank you, Madam Chair.
Thank you, Captain Smith. And I just want to briefly go over today's proceedings, which should conclude around 1 p.m. today. Today will be dedicated to Panel 2, Pylon Design Requirements, which we've broken down into 2 sections. We'll start this morning with testimony on Federal Aviation Administration Part 25, Design and Certification Requirements for Pylon Separation Failure Modes. That should wrap up around 10:30. Then we'll explore the design of aircraft systems routed through the near pylon attachment points, which will take us until about 1 p.m. We'll take breaks as needed throughout the day, and I just want to extend the same offer as yesterday. If parties or witnesses need a break, please feel free to just, I know the witnesses don't have electronic devices, but wave, signal you need a break. You all can do the same, and, we'll be flexible and make sure people have the time that they need. The process for panel 2 will be the same as yesterday. After an introduction from Mr. Shin, we'll move into witness testimony. The witnesses will be questioned in the following order. First by the NTSB technical panel, next by the parties to the hearing, and then by the Board of Inquiry. We'll circle back to the technical panel, and I do want to make sure everybody has a chance to ask all the questions they would like to ask, because this is the only hearing that will occur. So if parties have additional questions, we'll certainly come back to you as well, and the Board of Inquiry as well. On behalf of the board, I'd like to thank the witnesses testifying at the hearing in support of aviation safety. We ask that all witnesses be present until the conclusion of the hearing, unless you've coordinated in advance with Mr. Shin, the hearing officer. And that goes for yesterday's witnesses, as well as you may be recalled for further questioning. And usually that occurs when a question is asked or something's answered and somebody may not have an answer to something and need some assistance from a prior witness. Next, the hearing officer will describe the exhibits. Mr. Shin.
Thank you. Exhibits for this hearing include reports produced by NTSB investigative staff, videos, and other documents submitted by the technical panel members, witnesses, and parties to support the testimony and questions you will hear today. These exhibits for this hearing are in the docket, which opened to the public yesterday morning. A link to the docket is on our website, ntsb.gov. The docket can be accessed using the accident investigation number DCA 26MA024. That's Delta Charlie Alpha 26 Mike Alpha 024. If you've joined us in person, you can scan the QR code on the hearing agenda. This will take you to the investigation page. The link to the docket is on the right-hand side just below the map. The NTSB is authorized by statute to disclose information to carry out its mission, but we protect confidentiality and proprietary information to the extent possible. As such, exhibits contain redactions. These are the results of negotiations between the NTSB regarding the disclosure of information claimed to be personally identifiable, security sensitive, or proprietary in nature. Though redacted, exhibits contain sufficient information so that members of the public can refer to them during the hearing and throughout the NTSB investigation. The exhibits entered into the record and any presentations, along with other records of the investigation, become part of the NTSB public docket, which will remain available at ntsb.gov. We provided party spokespersons and witnesses with electronic copies of the exhibits in advance for the sole purpose of preparation for the hearing. A transcript of the testimony taken during the hearing will be prepared and entered into the docket as soon as possible. Mr. Eric Johnson will keep a list of additional documents admitted during the proceedings, and we will add these documents to the docket after the hearing concludes. As a reminder, new exhibits will be admitted only if the chair determines good cause has been shown as outlined in Title 49, Code of Federal Regulations, or CFR, Section 845.9. Chairwoman Hamidi, this concludes my remarks.
Thank you, Mr. Shin. We're now ready to begin panel 2. Will you please introduce the topics and the witnesses?
As mentioned, panel 2 will address pylon design requirements in 2 sections, starting with FAA Part 25 design and certification requirements for pylon separation failure modes. Specifically, we will question the witnesses in the following issue areas: transport category airplane design requirements, including requirements circa MD-11 certification and current requirements, and Boeing's design approach for the pylon attachment to the wing. The witnesses for panel 2 are composed of the following individuals, starting nearest to the board members. We have Mr. Todd Martin, Manager, Technical Policy Branch, Airframe Section, Federal Aviation Administration. Mr. Ken Fairhurst, Continued Operational Safety Technical Advisor for the Federal Aviation Administration. Mr. Justin Konopask, Director, Airframe Service Engineering, Boeing Commercial Airplanes. And Mr. Steve Chisholm, Vice President and Chief Engineer, Mechanical and Structural Engineering, Boeing Commercial Airplanes. Chairwoman Hamidi, these witnesses have been pre-qualified and their respective experience and qualifications appear in the docket.
Thank you, Mr. Shin. Now, Mr. Konopask, you were sworn in yesterday, so you do not need to stand. That, as I stated yesterday, that continues through the duration of the hearing. But if I can ask the other 3 witnesses to please stand. Thank you, and raise your right hand. Please answer by saying, "I do." Do you swear or affirm that the testimony you will give in this hearing will be the truth? Thank you. You may be seated. As a reminder to the witnesses, you will remain under oath until the conclusion of the hearing. We ask that you answer questions factually and not speculate. That's very important. If you think a question is speculative, please state that you believe it's speculative. The answer of "I don't know" is never a wrong answer. You can provide information for the record, and we'll be glad to take that. I just want to make that clear. And finally, just push, there's a microphone button. It says push. If you push it when you talk and bring it closer to you so that everybody can hear, that would be helpful. Mr. Shin. Oh, nope. It's going to Mrs. Oki.
Thank you, Chairwoman Hamidi. The following questions is for the FAA. Mr. Martin, can you please provide a high-level overview of airframe structure certification for Part 25 transport category airplanes?
Good morning. I guess I would summarize the structural requirements as 2 main sets of criteria: the design strength requirements and fatigue and damage tolerance requirements. There are other requirements, of course, but those are the main ones. To meet structural design strength requirements, the airplane must be capable of withstanding the design load conditions specified in the regulations. These include maneuver loads, gust loads, landing loads, and some failure conditions such as fan blade failure. To meet fatigue and damage tolerance requirements, the airplane must be capable of withstanding the repeated loads expected in service without failure due to fatigue, corrosion, and accidental damage. The fatigue and damage tolerance requirements they're contained in 25.571. And they've changed over the years since the certification of the MD-11 and even before then. But in general, a crack growth analysis, fatigue analysis, and test are used to show that no fatigue cracking will occur for the life of the airplane. The results of the fatigue and damage tolerance requirements are either a set of inspections, which are designed to ensure that any cracking occurring in service will be detected and corrected before it becomes critical, or replacement times are provided.
Thank you. Can you please describe the difference between a damage tolerant or a fail-safe concept?
Fail-safe is referring to multiple load path structure. And so for fail-safe structure, if one load path fails, then the remaining load paths or load path are shown capable of withstanding the limit loads that would be expected for the life of the airplane. Damage tolerant is a more recent requirement than fail safety, and the MD-11 did meet the damage tolerance requirements at the time. Damage tolerance requires inspections, like I was referring to earlier, for any cracking that could occur in service. So most damage tolerant structure is fail safe, but there's an additional element of inspection that's used.
You kind of mentioned that certification requirement change over time. In 1990, when the MD-11 was certified, can you please go over the requirement for static fatigue and damage tolerance?
So at the time, it was for static requirements, that would again be the design strength requirements. So all the Part 25 design load conditions would have been met. I'm not sure how much detail you want there, but
Was the MD-11 certified for fail-safe versus damage tolerance?
yeah, so first it met the design strength requirements, and then the next bucket is fatigue and damage tolerance. It was designed, as I understand, for fail safety. However, that was not the requirement at the time. Fail safe was a previous requirement. And by the time of the MD-11 certification, it was Amendment 54 of Part 25, and that included damage tolerance criteria. And so that's very similar to what's required today. It's a set of inspections, or the result will be for damage tolerant structure are a set of mandated inspections that are applied to the structure of the airplane.
Okay. And then you also mentioned that testing and analysis is required for certification. Is a full fatigue test or component test required?
At the time, full-scale fatigue testing was not required, but it was employed, I think, on the DC-10, and then the results of that testing were carried over to the MD-11. But technically, per the requirement, it's not required. Full-scale fatigue testing. Component testing is part of the analysis and is used to evaluate the structure.
Okay, thank you. We touched on the definition about PSC, or what a primary structure is, yesterday. Do you know if the definition is the same back in the 1990s?
Yes.
Okay. And then also from yesterday, Dr. Knapp mentioned that PSC designation is done during certification between the FAA and Boeing. But he also mentioned that it can change throughout the life of the aircraft. Can you say what would be a reason for a redesignation or changes of a PSC?
Usually when there are changes, it's to either reduce the inspection interval or threshold, or to extend it, not to change the designation of PSE to not PSE or vice versa. But that could be done. That would be a certification project. An element could be designated, let's say it's not designated as a PSE today, but after further review, it is decided that it should be a PSE. That would be a certification project, and we would review the primarily the compliance data for 25571, make the determination, and then establish the inspections. And then in order to, that would just be a certification project, but in order to mandate those for the fleet, an AD would be required, airworthiness directive.
Thank you, Mr. Martin. I'll hand it over to Mr. Cruikshanks.
Thanks. Good morning. So now I'm going to turn to Boeing and we'll talk about how did you comply with these requirements that the FAA just told us about. So yesterday we talked about, we defined what a primary structure is, what a principal structural element is. So I don't think we need to define them again. But can you tell us which components on the MD-11 pylon are considered PSEs or principal structural elements?
The principal structural elements on the MD-11 pylon, I'm going to speak to what I know with absolute certainty is that the pylon forward bulkhead, the thrust link, and the pylon aft bulkhead are considered principal structural elements. With respect to the other elements on the pylon box and the engine attach points, I would want to follow up with that detail. If that's okay. I'm not sure on that one for sure.
Okay, no, that's good. So the pylon aft bulkhead and the lugs are considered a principal structural element.
That is correct, yes.
Okay. How did Boeing go about deciding which components were considered PSEs during the design of the MD-11?
The principal structural elements, ROAR identified based on the subset of primary structure, the principal structural elements, which were determined to be essential for continued safe flight and landing. And those were what was identified as those principal structural elements.
Okay, so you mentioned ROAR. Just for everybody's clarification, can you explain the relationship between ROAR and Boeing at the time of design of the MD-11?
Yes, absolutely. There was a statement of work provided between the Douglas Aircraft Company at the time, or McDonnell Douglas, to ROAR, who's a supplier, if you will, in this situation, to ultimately perform a large portion of the design and analysis and testing associated with the certification of the MD-11 pylon. And so the McDonnell Douglas Company handed over certain requirements and had certain aspects that they took into account, such as providing external loads, and then ROAR consumed that data and then performed a subset of tasks to support the overall certification.
Okay, thanks. Can you give us any information on why the pylon aft bulkhead spherical bearing was not considered a PSE during the design?
I don't have any record that clearly documents the spherical bearing decision of not being a principal structural element. So anything I would say would be speculation at this time.
Okay, but we know that it was not considered a PSE for this design.
That is correct, yes.
Okay, thanks. Next, I want to touch on some of the design philosophies. So first of all, can you explain kind of at a high level the design philosophy for an MD-11 pylon and how it evolved from, say, the DC-10?
Yes, the attachments between the DC-10 and MD-11 stayed consistent. I think visually I can use that to, if we go to Exhibit 7U, page 2, that would be a good representation of the attach points. Next page, please. Thank you. The visual on the left-hand side is what I'm referring to with respect to the attach points. What you see on the left-hand side is considered the pylon forward bulkhead that has 2 attach points to the front spar of the wing. Just behind that is the thrust link, and then the pylon aft bulkhead is further to the right side of that structure. And so those attach points were prescribed as being similar to the same as the DC-10 to the MD-11.
what were the major differences between the MD-11 pylon and the DC-10 pylon?
With respect to the differences, one of the key differences was the engine configuration. The MD-11 has larger engines, different attaching mounts on the pylon structure itself. If you'd like, I'm happy to describe the differences as well for the pylon aft bulkhead specifically between the two.
Yeah, how about just for the pylon aft bulkhead?
Yes. The DC-10, similar design in terms of back-to-back structure. One of the main differences is that on the DC-10, the aft half of the assembly didn't extend all the way down the full length of the bulkhead. It stopped partway down, about 2/3 down the structure. Additionally, the material on the MD-11 is back-to-back forging material as opposed to forging in plate on the DC-10. And then there are some other differences with respect to the fasteners on the side as it extends to the pylon skins, the forward flange of the bulkhead as well around the radius area was slightly modified and adjusted. And then the last item being the MD-11 pylon at time of production also had the lubricated bearing that we've been referring to.
Thanks. So now, can you tell us how Boeing complied with the requirements, the FAA requirements for static, fatigue, and damage tolerance at the time of certification in 1990?
Yes. So I'll break it into sections here because I know there's going to a lot of material in that question. And so I think if there's anything you want to further dive into, please let me know. With respect to static strength requirements, as I mentioned, McDonnell Douglas provided the external loads, which were consumed by ROAR and ultimately developed internal load cases that supported the static strength analysis. Specifically, when it comes to the static strength, there was a fan blade out condition for the Pratt & Whitney engines that was used in a large way to envelope the GE conditions for static strength. And so that was used for the analysis, and then as well in terms of testing, there was a pylon-proof loading test that was performed, which validated that the structure, I believe over 11 different conditions, was capable of maintaining certain load conditions, about half being limit load and then the other half being a handful of other configurations. Moving on to fatigue. The fatigue spectrum, if you will, was calculated or created. I think to explain that, I'd like to pull up a visual, actually, if that's okay. Could you please bring up page 5 of Exhibit 7U? Thank you. Fatigue, as defined in the center, is really defining the operational envelope of the aircraft. And not every flight is considered the same. And so this takes into account variation of flights that may occur over the life cycle of the aircraft and creates what's called the fatigue spectrum to then calculate the respective loads on different structure. And so we had analysis performed, which, as I mentioned, for the pylon aft bulkhead calculated the fatigue life of 87,800 cycles and then factored down to that 29,200 cycles. There was also a test performed. This wasn't a full-scale fatigue test, as the gentleman from the FAA had prescribed. This was a assembly level test is the best way I can describe it. So the bearing was actually installed into the aft pylon bulkhead assembly, and then that was cycled in a way that was reflective of the loading spectrum on for that structure, and that cycled up to 84,000 cycles, or 2.8 times the design service objective of the aircraft, with no findings. Moving on to the damage tolerance aspect of it, the damage tolerance assumes. Thank you. If a crack exists, we want to make sure that we have ample opportunities to detect that crack before it becomes critical. The definition of critical would be understood as under a limit load or residual strength application, the structure is no longer able to carry that type of loading condition. And so with respect to the pylon aft bulkhead, there were several flaws initiated in this analysis, and then you cycle through a spectrum load that would create the most critical damage to that crack. In that particular occasion, it was a certain flight that occurred most on the GE spectrum. And so that's what was utilized as outlined in the exhibit here, structures exhibit. And then ultimately that gives you the respective time from crack initiation, or the flaw initiation, that's a better way to say it, to when it would be detectable and then it would be critical. And then ultimately that feeds into what your repeat inspection would be once you hit that fatigue threshold.
Okay, thanks. So you mentioned some of the testing that was done, and I want to dive a little bit more into the fatigue test that was done for the aft bulkhead. And can you kind of go a little bit more in detail about how that was done? You mentioned it went to 2.8 lifetimes, and then was there inspections performed throughout that test? Did you find any cracking, and what was the end result?
The pylon was visually inspected throughout the life of that program, that test, if you will. There was also a lubrication task of the bearing that occurred. I don't know the exact number of flight cycles, but I believe it was per the required specification for that lubrication task to ensure that the bearing was operating as intended. And so at the end of that 84,000 cycle tests, the structure was examined and there was no any sort of defect that was found. And so at the conclusion of the fatigue test, the team did load that in compression yield test, if you will. And so you apply a lot of load in a downward force. I think it was right around 125,000 pounds. And that structure did not show any signs of deformation or failure during that aspect of the test. And then at the conclusion of the entire test, they pulled the part in tension, if you will, loaded it in ultimate tension, and that's where the lugs were found to fail at 180,000 pounds.
How did that 180,000 pounds compare to the design loads?
Significantly higher than the design loads.
Okay, thank you. Was the pylon aft bulkhead spherical bearing analyzed at all during the certification in 1990?
The analysis that was performed would be a static strength analysis. The fatigue test was used, as well as the qualification test, which I described yesterday, performed or prescribed by the vendor, which reached up to 120% of ultimate load for both the axial and radial directions.
Okay, and I think you touched on this a little bit, but the MD-11 was certified to be equipped with either a Pratt & Whitney engine or a GE engine. And so you have different loading conditions. How were those taken into account in the design?
Yes, specifically for the pylon aft bulkhead, the critical load condition that was utilized was the Pratt & Whitney fan blade out condition. The fan blade out being that significant event, more specifically at the engine mounts. That load was actually utilized in the pylon aft bulkhead as well, and so some ways away it was a significantly higher load than what we would use today. The crack growth analysis, or the damage tolerance, that's when you review, you have to interrogate the structure to understand how a crack might begin to propagate in that structure and when it would reach critical length, under what flight conditions. And so that's where the team identified there was a specific maneuver in the GE load spectrum that was utilized to support the damage tolerance analysis.
Okay, thanks. So I think Mr. Martin touched on this, but there was a fail-safe analysis done on the pylon aft bulkhead. It was not a certification requirement, but can you kind of talk to us a little bit about why that was done and what the results were?
Yes, absolutely. The fail-safe requirement, it was design criteria, which is extended from the DC-10. It's not uncommon to have a design criteria from an airframe manufacturer of fail safety, where just damage tolerance is a certification requirement. To explain what was considered for fail safety, specifically in the pylon aft bulkhead, I'd like to use an exhibit. If we can go to 7U, page 3, please. Thank you. This represents a view looking forward, or sorry, it's looking inboard, outboard, apologies about that, of the pylon aft bulkhead. The items that were considered in the fail safety design, I will call out the name as well as the color. The light blue clevis fitting, and so it was analyzed that either side, either one of those lug fit portions of the clevis fitting could fail, and the other could maintain limit load. Additionally, not shown on this page associated with the clevis fitting was also examined the bolts that install the clevis fitting specifically onto the lower wing skin. Moving on to the aft pylon bulkhead lugs, represented in a dark blue color here. It was analyzed and confirmed that under the limit load condition, if one lug failed, the other would be able to maintain limit load for a period of time as well. And then moving on to the bushing and bolt configuration, it was analyzed that if the bushing failed, the bolt would be able to maintain the respective strength to maintain limit load.
Okay, so you mentioned limit load a couple of times there. Can you just define for us what that means?
Yes, apologies about that. Limit load represents the highest load that structure may experience in the entirety of operations, we'll say that. And so when you think about limit load, you want to think about a very extreme or aggressive maneuver that would really stress the structure. It would put a lot of load on the structure. For this particular structure, it's what's called like a 2G flaps down maneuver. And so you think of a very strong pulling up motion, if you will, on the pylon. The ultimate load, which I've used that as well, and I'll just define that here. Ultimate load is what we ultimately certify the structure to for static strength, which represents 150% of limit load.
Great, thanks. So I'm going to turn it over to Mrs. Oki. She's got some questions.
Hi, back to Mr. Martin. I have a few questions for you. What were the FAA certification requirement for Part 25 transport category aircraft to ensure safe separation of wing-mounted engines in an emergency landing situation back in the 1990?
The only requirement at that time was 25-994, which was a wheels up landing requirement, and required that there not be hazardous amounts of fuel spilled in the event of a wheels up landing on a paved runway.
And what is the historical basis for this regulation?
I don't know the historical basis. I mean, wheels up landing events had occurred before then, but it was introduced in the early 1970s, Amendment 23 of Part 25, that requirement.
Has this evolved as far as a requirement since the 1990?
Yes, in 2014, there was a small change to that requirement where we specified that the descent rate for a wheels up landing would be 5 feet per second. And there are other related updates to pylon separation requirements, if you want me to
Yes, please.
touch on those. So in 25-721, at the same time we added the 5 feet per second requirement to the 994 wheels up landing, we also added a nacelle or engine breakaway requirement that said that similarly, there should not be hazardous amounts of fuel spilled in the event of a wing-mounted engine tearing away during a heavy landing with the loads acting in the up or aft direction.
Are gear up landings, or you said hard landing, the only requirement as far as engine or pylon separation considered for?
Yes.
Yeah. Okay. And then is there any other changes? Go ahead.
Just to clarify, the engine breakaway requirement does not assume wheels up. It's just a breakaway requirement. But it is a landing situation.
Okay. And then you said that occurred in 2014?
Yes.
Okay, that's it. I'll hand it over to Mr. Cruikshanks.
Okay, thanks. So just to be clear, Mr. Martin, the engine separation is only for an emergency landing condition and no other condition in the life of the airplane?
Correct.
Okay, thank you. So now to Boeing, let's talk about how you complied with these regulations during the certification. So can you talk to us about how you complied with the safe separation of wing-mounted engines during the emergency landing conditions?
Yes, and I will address each case separately. I'm going to refer to visuals as I think that's easier to talk to. If we can start with Exhibit 7X, Figure 1, please. And as that exhibit's being pulled up, I'll define a little bit of terms here that I'll probably use throughout the duration of this discussion here. The means by which compliance is shown, or the design approach, if you will, to satisfy the requirements is connected to what are called structural fuses. And the intent of a structural fuse is to ensure the integrity of the fuel tank is maintained during these types of conditions, these emergency landing conditions. And so that's what I'm going to be talking about through these different scenarios, the structural fuse locations as it relates to meeting the requirements. So during a hard landing, while it wasn't explicitly defined as a certification requirement at the time, it was part of the design consideration for the MD-11. What's shown here visually is where the structural fuse is located for that condition, and that is on the forward part of the pylon, just it's called the truss there, if you will. And so during that condition, the force or inertia of the engine coming down, the margin of safety difference, or the strength difference, if you will, between the location that I have identified as the structural fuse for the hard landing versus the top right section of that image, that's where the fuel tank is and where that pylon forward bulkhead attaches to the wing, it is sufficient enough such that the truss will fuse and then the engine will be able to break away in a way that protects the fuel tank. If we move on to Figure 2 of the same exhibit. Thank you. This represents what would be expected in terms of the wheels up landing condition. During this condition, the engine is making contact with the ground first as the aircraft lands. During that condition, the engine you need to have a method for such that it's able to break away from the fuel tank, again, ensuring integrity of that fuel tank. And so the structural fuse at this location is defined as the pylon aft bulkhead, specifically the lugs, which we have tested as well in terms of the system, that 180,000 pound test that would exceed the material capability of those lugs. If you scroll down to Figure 3, what you see is the associated reaction of the pylon forward bulkhead and then the thrust link during this condition, because the engine pivots but maintains attached. The pylon forward bulkhead yields right just above the pylon box area, if you will, and then the thrust link kind of pivots in that situation.
Okay, thanks. can you just talk a little bit about the difference in design philosophy from the McDonnell Douglas airplanes to the historical Boeing North airplanes?
Yeah, I'll speak to that, Mr. Cruikshanks. Mr. Konopask talked about fuses, and he talked about fail-safe applications. Both of those at the highest level, if you look at the design philosophy, it's consistent between our Heritage Boeing models and Heritage McDonnell Douglas. Both utilize structural fuses, both maintain fail safety even when certifying damage tolerant. The specific application of that does look different. The architecture is different. On Heritage Boeing products, sometimes called 7 series airplanes, there are discrete elements that we call fuse pins, rather than relying on a structural overload and a difference in margin of safety between structural components. We prescribe the capability of a fuse pin. The intent is the same.
Great, thanks for that. Now we're going to go to Mrs. Oki so she can talk about to the FAA about maintenance requirements.
All right, Mr. Martin, back to you. What were the certification requirements to maintain continued airworthiness of principal structural elements and primary structure back in the 1990s?
So from a certification standpoint, it would again be the fatigue and damage tolerance requirements of 25571. And those requirements would ensure the development of a set of inspections, mandated inspections for the principal structural elements on the airplane.
Was there any changes after 1990?
To the requirements in general or the main?
For continued airworthiness as far as maintaining the aircraft with the principal structural elements?
I mean, the methods by which you develop the inspections have changed, but the fundamental requirement that there be inspections and that they are designed to detect cracking before it becomes critical, that's remained the same.
What maintenance documents is required part of certification?
It's called the airworthiness limitation section. It's referenced in Part 25, Appendix H.
Is that an approved document?
It's an approved and mandated document, yes.
Is there any other manufacturer maintenance documents requires FAA approval versus acceptance?
The terminology approved versus acceptance changes a little bit, and I guess I don't want to speak to that, but there are other maintenance requirements. There's the aircraft maintenance manual. There's a set of inspections, some of which can be escalated throughout the operational life of an airplane, but the airworthiness limitations is sort of a standalone document that's mandated and closely controlled.
And then you mentioned it can be escalated or maybe de-escalated. What is the requirement as far as getting that approval from the FAA?
For the anything that's a principal structural element, to get it escalated, to get those inspections escalated would require a certification project and a showing of compliance to 25571.
Would that be more based on analysis, not testing, or any other requirement as far as the certification plan?
It could be analysis, test, or in-service findings can also be considered.
Okay, thank you. Back to you, Mr. Cruikshanks.
Thanks. So I think we'd like to get your definition or the FAA's definition of accepted versus approved. Those are two different things. So we definitely would like to know what those are.
Okay, we'll take an action on that one.
Okay, thank you. So, Mr. Martin, if I heard you correctly, the required maintenance documents for certification are what we call the airworthiness limitations instructions, and those are in the instructions for continued airworthiness. Is there any other required maintenance documents for the aircraft at certification?
Yes, there's many different ICAs required for maintenance in general, but for
Specifically, maintenance on principal structural elements.
no, it's limited to that area.
Okay, and is every PSC inspection contained in the ALI?
It's possible that there are some inspections that would be designed for the PSE, but that would be included in general maintenance because it's basically determined that no specific inspection is necessary in the airworthiness limitation section if those inspections are already included in the general maintenance and the thresholds and intervals are such that it's unlikely to be exceed the intervals and thresholds determined for compliance to 25571.
Okay.
For the most part, everything that's a PSE is in the airworthiness limitation section.
Okay, thanks. So now to Boeing. Let's talk about how the airworthiness limitation instructions and the inspections of PSE, specifically the aft bulkhead lugs, how those were developed and the evolution of that, how you met that certification requirement.
Yes. So going back to, I'll briefly cover some of the discussion that we had yesterday, and then feel free if there's any other areas we want to get into more detail. So at the time of certification, specifically the Pylon aft bulkhead lugs had a threshold of 19,900 cycles. The actual threshold as calculated by the baseline certification analysis for the fatigue life of these parts was approximately 29,200 cycles. The 19,900 was defined in accordance with having an inspection prior to the design service objective, which was a requirement at the time as part of certification. Actually, I'll pause there if there's any other questions, but I think that covers it.
So that 19,900 cycle number, that came as a requirement from the FAA? Is that right?
Yes, it was prescribed to have one inspection prior to reaching the design service objective.
Okay. But the fatigue analysis showed that the first inspection should occur when on the Pylon aft bulkhead lugs?
Based on the fatigue analysis, it would be 29,200 flight cycles.
Okay, thanks. Now we can, I think that's the questions there. So let's move on. How did that document evolve over time?
That document has a number of, I'd say, revisions over its history. And so I'll cover a few of them to the best of my knowledge. It was originally part of the certification of the aircraft. There was an airworthiness directive in 2007 that was mentioned yesterday, which covered an adjustment in threshold and repeat interval for different PSEs, if you will. And the only way to adjust the airworthiness limitation inspections is by some sort of approved method. And so in this situation, it was an airworthiness directive. Fast forward to, I believe it was approximately 2015. The Boeing company put together a certification package to adjust a handful of principal structural element thresholds and ultimately leverage the baseline certification analysis for those thresholds in support of operators' maintenance programs, such that they were able to align as many of them were, I'd say, out of sequence from the regular heavy maintenance tasks. And so at that time, there was a certification plan put together and then an alternative method of compliance provided by the FAA in support of the revision to the thresholds.
And so specifically, how did the aft bulkhead lug inspection change?
The threshold was elevated from 19,900 cycles to 29,200 cycles circa 2015.
Okay. Can you tell me a little bit about what inspections are required in the ALI for the pylon aft bulkhead lugs?
Yes, there are 3 specific inspections. The first one being an ultrasonic shear wave inspection. This is done externally on the surface. And then there are 2 eddy current or high frequency eddy current inspections, which are performed, one being on the face of the lugs, and then another one being the bottom radius of the lugs.
And are those inspections designed to be performed on wing, or does the pylon have to come off?
They are designed to be performed on wing.
Mrs. Oki has a question.
Just to follow up, Mr. Konopask, you mentioned design service goal. What was the DSO for the MD-11?
The design service objective was 20,000 flight cycles and I believe 60,000 flight hours.
Has that changed?
No, it has not.
Okay, thank you.
I have a couple follow-up questions. For Mr. Martin, for the Part 25, I believe you said it was 25.994 for the wheels up landing condition. Is that correct? Are there any engine thrust loads assumed or required when doing that wheels up landing, or is it assumed to be idle?
We don't have any guidance, as far as I recall, on what the thrust rating should be. And it's not in the regulation.
Okay. And is that the same for the engine breakaway condition?
Yes.
Okay, thank you. And for Mr. Konopask, similar question to you. Does Boeing have any objectives for meeting those regulations in terms of the thrust loads or ratings that that you would use?
I don't know if that information was considered.
Is it considered with the current designs?
I don't know.
Can we get that as an IOU?
Yes.
Thank you. And then for the fatigue testing of the pylon assembly, at the end of that fatigue testing, is Boeing aware if that bearing was ever removed and examined, even though the lugs didn't crack or show any evidence of fatigue? Did the bearing get removed and inspected?
To the best of my knowledge, the bearing was not removed. Once the bearing is installed, the staking process to install it, you're unable to remove it and then reinstall it and achieve that same installation.
Okay. So not asking you to speculate about the fatigue test done back then, but if one was done now with a pylon with a bearing in it, and the bearing is not considered a PSE or principal structural element, if that bearing were to fail during fatigue testing that's aimed for the actual structure itself, for the principal structural elements, what's Boeing's approach in resolving that? What are the options, and what options would you use for that testing?
We would absolutely want to understand the cause of that failure, investigate that root cause, and really make sure that we're able to resolve that going forward, and likely perform follow-up testing and/or analysis.
And would that follow-up include either a redesign of the bearing, or would an approach of mandating inspections of the bearing and having it again as a consumable, replaceable item in service be considered?
That would depend on the installation and design itself, the intended use. A bearing acts as an interface primarily to the broader structure that it's installed in. And so it's hard for me to answer that without really understanding the design and the intent of the application.
Thank you. Chair Hamidi, that's the tech panel's questions.
Great, thank you so much. We're going to continue. Does anyone need a break? All right, we'll go through party questions and we'll take a brief break before the Board of Inquiry questions, and we'll start with Boeing. Ms. Widener.
Thank you, Chair Hamidi. We have no questions.
Thank you. Federal Aviation Administration.
Thank you. We have just one for Boeing. What was the pass-fail criteria for subcomponent fatigue testing for the aft pylon?
To the best of my knowledge, the pass-fail criteria was a detailed inspection of the structure for any sort of fatigue cracking or damage that may exist or deformation that may exist throughout the life cycle of that particular test.
Okay, thank you. That's all the questions we have.
Thank you, Mr. Kabek. Teamsters.
No questions.
Thank you, Mr. Landis. STE San Antonio Aerospace.
No questions?
Thank you, Mr. Hens. Captain Smith.
Good morning, thank you. This question pertains to FAA or Boeing, either one. We've heard that the lugs were fail-safe. The accident establishes that the lugs were not fail-safe, isn't that correct?
Captain Smith, can you repeat the question? We're having
Yeah.
trouble. I don't know
Sorry.
if it's because you're facing the other way. We're having trouble hearing
Okay.
your questions.
Sure, I'll rephrase it here and speak up a bit. Does that seem better? Okay. So we heard over the last few days that the lugs were fail-safe. The accident establishes that the lugs were not fail-safe. Is that correct?
So I would not agree. Fail-safe only means that if you fail one element, so the forward or the aft lug, that the other element would be able to maintain limit load. I think what happened in this case is that both lugs failed simultaneously due to the situation with the spherical bearing. So it's not technically whether that proves it was fail-safe or not is, I don't think we can say.
Okay, I'll continue on for the FAA. We heard that the spherical bearing was not a PSE, and that even now, after the accident, the bearing is still not considered a PSE. Is that correct?
That's what Boeing said yesterday.
So given the number of occurrences of spherical bearing damage accompanied by lug bore damage known to Boeing, isn't it clear that the spherical bearing should have been designated as a PSE by Boeing?
So I anticipated this question, and so I wanted to write down my answer to make sure I say this clearly. Whether the spherical bearing is a PSE or not depends on the consequence of its failure. Is integrity of the bearing essential to maintain the overall structural integrity of the airplane? Failure of the spherical bearing does not directly result in failure of the aft lugs, which are PSEs. However, it appears that failure of the bearing could adversely affect the fatigue capability of the aft lugs, and therefore it should be considered a PSE. I would just note that I agree with what Boeing said yesterday, that it's not intuitive or obvious that failure of the bearing or race would impact or adversely affect the aft lugs. So the decision back in 1990 could be seen as reasonable, but given what happened in this case, it seems that the failure of the bearing, like I said, affected the aft lugs and therefore should be considered a PSE.
Okay, another question for the FAA. Yesterday, we heard Mr. Hirsch from Boeing say you would not expect bearing damage unless there was also migration. But we know from the Structures Group Chair report, page 57, it talks about Operator 3, that in February 2009, Boeing knew that a spherical bearing could be damaged, but not migrated. So if the bearing had been a PSE, isn't it correct that there should also have been an inspection procedure for spherical bearing damage, whether or not there was visible migration?
If the spherical bearing were designated as a PSE, then it would either be considered or defined as damage tolerant structure or safe life, meaning safe life means a life limit would be applied. So if there's no reasonable inspection method that could detect cracking, then a life limit is applied and it's considered safe life structure. So if it were determined to be a PSE, there would either be an inspection, an appropriate inspection, or a life limit applied.
Thank you.
All right, well, we'll go through again just to see. Ms. Widener,
Thank you. No questions.
Federal Aviation Administration, Mr. Kabeck.
No questions at this time.
Mr. Landis, Teamsters.
No questions.
Mr. Hens, STE Engineer, San Antonio Aerospace.
No questions.
And Captain David Smith.
Thank you. No further questions.
All righty. We will move on to the Board of Inquiry. Why don't we take a 15-minute break? We'll come back at 9:30. Hi, we're going to stay on break for another 10 minutes. If you don't mind, we'll be back at 9:40. All right, thank you for your patience, appreciate it. And we'll get started with the Board of Inquiry. And today we're going to start with Member DeLue.
Thank you, Chairwoman Hamidi. I'd like to start by asking if I can have the exemplar bulkhead brought up to reference for my questions. And can I ask that photos of the bulkhead be entered as an exhibit?
Yes.
Thank you.
Those will be entered as photos of the aft bulkhead will be included in the exhibits.
Thank you very much. For everybody's information, this is Chris Wallace, my special assistant. Thank you, Chris. All right. It's not all that heavy, but can you also put up the exhibit 7 uniform, which is the picture of the that one, also the color coded that we had earlier. Perfect, thank you. So let me just start by first showing this bulkhead here, but Mr. Martin, thank you for your written statement that you read prior to the break. Would you please reread that? I want to make sure I heard you correctly and take your time, but I appreciate you put that prepared.
Sure. So what I said before was whether the spherical bearing is a PSE or not depends on the consequence of its failure. Is integrity of the bearing essential to maintain the overall structural integrity of the airplane? And if so, then it's a PSE. Failure of the spherical bearing does not directly result in failure of the aft lugs, which are PSEs. However, it appears that failure of the bearing could adversely affect the fatigue capability of the aft lugs, and therefore it should be considered a PSE.
Thank you very much.
Sure.
So I think for everybody's benefit, as you know, we're all looking into something new here. This is, you know, a new world we're going into for most of us in the room. So this, and I guess this will be for Boeing, this part here, the green, the entire 2 plates, and these are the lugs that we refer to at the fore and aft. What is the material? Is this steel, titanium, aluminum? What is it?
It is aluminum forging.
Okay, so aluminum. So these lugs are aluminum. Obviously, the bearing is steel.
Yes, it is.
And the race is also steel.
Correct.
So just out of curiosity, if this bulkhead was made out of titanium, for instance, would that have been would have been a different certification, but more fail-safe, let's say?
Any sort of material change, you'd have to look at the entirety of the impact. And so, you know, I don't know specifically why certain material choices were made at the time. If you refer back to what I mentioned as well, if you did change that material, you'd have to consider all aspects of it, such as the requirements for the breakaway or the structural fuse, if you will.
Okay, and I get it was back in the 90s. So this, but the design of this was that, and I think Mr. Martin said it's the terminology is fail-safe, and I recognize what you meant by that, but the design was that if this forward lug was to break, for instance, or fracture, the aft lug should be able to maintain and stay in place, correct?
Correct.
So, and at the time, this was the aluminum that was designed and it was certified, correct? This piece here.
Correct.
Just out of curiosity, let's say I want to build an airplane tomorrow and use this thing. Is this available or is this a patented? What is this? Does somebody own the patent on this?
I don't know specifically the Pylon aft bulkhead. I believe there is a patent on the Pylon design itself, but with respect to how detailed it gets, that goes above my knowledge.
Okay, I just don't know if this is, so are there other aircraft flying around that have a similar design? I mean, I know you can't speak for other manufacturers, but does Boeing have other aircraft flying that have the same type of design?
To the best of my knowledge, that particular design is associated with the DC-10, MD-10, and MD-11, with some variations in there, as I described earlier.
Okay, so if we've narrowed it down to where it's just this, we shouldn't see this type of failure on another type of pylon, correct?
Correct.
Okay, great. All right, my time's almost up. Thank you, and I'll have more questions afterwards. Thank you.
All right. Back to me, I guess. Thank you. Actually, I'm going to hold, and I'm going to go to Vice Chairman Graham.
Thank you, Chair. I want to talk a little bit about the phase of flight in which the pylon separated, which was takeoff. The spherical bearing in the aft bulkhead is designed to carry the weight of the engine while on the ground. Is that correct?
That is correct, yes.
Okay, and then in flight, the bearing is meant to carry the vertical, lateral, and torsional loads. Is that correct?
I'd like to clarify if that's okay. So that the bearing acts as an interface for the lugs. Inherently throughout the phases of flight, the pylon box will move to a certain extent, either through thermal expansion and contraction or just the loads that it's experiencing, which ultimately supports the fatigue life of the structure. And the lugs themselves are ultimately what are reacting the loads that you described.
Okay, so I'm going to go back and talk a little bit about the DC-10 accident also in 1979. While the circumstances surrounding the two accidents are not necessarily the same, as we know, we saw the engine pylon separate from the DC-10 back in 79, just after takeoff also. With what we know between these two accidents, do you believe the pylon separation, why do you believe the pylon separated in this phase of flight right after takeoff? Do you have any idea?
The details that we've received as part of this investigation so far indicate fatigue cracking on the lugs, and it is aligned with a condition known as tension, which this puts into there. And I have an exhibit that I can actually pull up that represents this. If you go to 7U, slide 4, please. Thank you. So during takeoff, when you have engine thrust being applied, think of the pylon as a teeter-totter, if you will, where the pylon forward bulkhead is acting in compression and it's rotating around that. The engine's it's applying thrust, and so then it's going to pull down on the pylon aft bulkhead, applying it in tension. And so the highest amount of tension as defined in the damage tolerance occurs at that condition or that phase of flight on takeoff and rotation.
Okay, so that's the more critical load, is the one in tension than in compression?
Yes, that is correct.
Okay. So would it be possible, what about in-flight cruise altitude? What kind of loads, do you know what kind of loads are on that aft lug?
I don't know the exact magnitudes, but to, I guess, explain the phases of flight as it relates to tension on the pylon aft bulkhead, after rotation and it starts climbing, once the flaps are retracted, that structure starts moving back towards compression quite quickly.
Okay. What's the more critical load, compression or tension?
As defined in our crack growth analysis, is that it's in tension.
Okay. So in the modes where for separation of the fuse plug on a hard landing or on a wheels up landing, the way I saw the picture, does that aft bulkhead break off in tension?
On the wheels up landing, yes, it does.
It does break off in tension. Okay. All right. I see my time's about up. Thank you for that.
Member Chapman.
Thank you, Chair. Mr. Martin, I want to follow up a little bit on the issue of fail-safe, and I'm going to confess to you I am well outside my comfort zone here with these topics, so bear with me. I believe you defined fail-safe, which was very helpful because I haven't really understood this fully myself. The last couple of days there's been a lot of discussion of fail-safe, but I believe you just defined that as a design that results in multiple pathways for bearing load, so that if one pathway fails, there's an alternative pathway for that load to be picked up, at least for some period of time. And do I have that correct? Is that right?
Yes.
The UPS folks asked the question about the design of the lug, which, by the way, for those in the room here, the UPS folks provided this example up here. You're welcome to come up and take a look. Just don't feed the board members while you're up here. But you're welcome to come up and take a look. It's very interesting. I think it'll help you gain a perspective on what we're talking about. The design here, it's a back-to-back plate. And so the idea was that if one of the lugs or one of the plates failed, the other, at least for a time, would essentially step in and pick up that load. The UPS question was, doesn't the fact that the two lugs failed simultaneously in the accident sequence, doesn't that establish that this was not a fail-safe, ultimately proved not to be a fail-safe design? And I have to say, just based on my very rudimentary understanding of that, that rings true to me, that even if the intended design was fail-safe, that in the real world experience of what we saw here in the accident, with the two lugs failing simultaneously under essentially the same load, that establishes that fail-safe design ultimately wasn't fail-safe. Am I missing something?
Well, so when I'm talking about fail-safe, I'm speaking theoretically, really. It's the definition of what fail-safe means. So fail-safe means one of those lugs, if failed, the other lug can take limit load. What the accident proves is that the design failed, not that it wasn't designed as fail-safe. I know it's a little bit of semantics, but there are issues with other fail-safe designs where you have to be careful, because there can be like a common cause failure where both lugs can be loaded at the same time for the same life and have the same deficiency, and so they both fail at the same time. So it's a matter of designing it properly to make the fail safety work. But from a theoretical standpoint, it's still a fail-safe design. But one reason we moved to damage tolerance and got away from fail safety was that kind of question, is because just because you design it as fail-safe doesn't mean it's going to last for the life of the airplane.
That's helpful, and I don't want to put words in Captain Smith's mouth, but I think the question was, if it failed, it wasn't fail-safe. What you're saying is that doesn't mean that the design wasn't intended to be fail-safe. It just ultimately proved not to be a fail-safe design. Is that right?
It was still a fail-safe design, but if, for example, if it was found that one of the lugs did fail first, and that the second lug was not able to carry limit load, then that would prove that it was not a fail-safe design.
Okay. All right. I was a music major in college, so this is outside my zone, but I appreciate the discussion there. And can I just, actually, I have some other questions. I'll hold those for later. Thank you, Chair.
Member DeLue.
Yeah, I'd like to just continue on with that line of questioning. So now that and I appreciate the way you phrased the answer, and I know it's kind of a semantic somewhat, But at the end of the day, we would probably say that if we had to redo this and get it certified, it'd probably be a primary structural element, correct?
Yes.
Our principal, I should say. So this part, I don't want to speculate here, but I understand that the MD-11 is flying again now at another carrier. So with that carrier, is that bearing now a principal structural element?
As far as I know, there's going to be, it will be flying again for us. I don't know the status of whether that's a certification project to allow it to continue to fly. There would have been an AMOC, alternative means of compliance to the airworthiness directive. That should require a certification project, which means the FAA would have to evaluate Boeing's compliance with 25571 and the fatigue and damage tolerance requirements. So then we would look at, yesterday there was mentioned a life limit of 4,000 cycles, I believe. We'd have to look at that and evaluate whether that's showing compliance with the regulation. And as part of that, there will have to be a decision on whether it is classified as a PSE or not.
So that's an ongoing process as we speak then?
I believe so. I'm not sure of the status of the certification project.
No, that's fair enough. Question though is as we went forward and we had this unfortunate accident, but it seems like it took an accident for us to start talking and asking these questions. So would there have been a point, I would like to think there would have been a point where these issues with the bearing would have been identified to see what you had mentioned that could potentially make these lugs no longer be fail-safe. Does the FAA proactively start saying, maybe we should take a look at this? Where does that process start where we say, whether it was from the manufacturer or from the regulator, to say, maybe we need to look at this, this should be a principal structure element, or because we basically are at that point, but it took an accident to get there. So can you kind of let me know what the process would be? And Ken, maybe you can tell us.
Yeah, good morning. The reassessment of once a product is certified, it's out of the certification realm and into a continued operational safety realm. And yesterday's hearing, panel 1 hearing, really was focusing on the cases of reports of failures and indications of failures. And I think the reinforcing of that is what could lead to implementing inspection requirements or implementing replacement requirements, whatever that might be. And yesterday's panel was really focused on that part of it and how that could be, what happened and how to get better about that. But as far as recertifying, that's not really what we do. Once it's certified, it's really the continued operational safety that would be required. Now, for the planes that have returned to service, they did have to go through an approval to have the new design and the new inspection, the replacement interval implemented. That would have to go through the certification process. But then once that's done, then that becomes the method of compliance that lets the aircraft get back into service.
Okay, so just to follow up, we got a minute here, but the continuation of operational safety. So if we would have had better data, more clarity in the data, that would have said, ooh, these bearings could fail, which could ultimately affect the lugs. That part of relooking at making this a principal structure element, that would not have been done by the certification branch, that would have been done by the cost part of the FAA?
We're in the same organization, but yes. Yeah. And Dr. Violet was talking yesterday about it, that part of it was to have the better data, but it was also to have the better understanding of the failure mode and the sequence of how this could play through to an unsafe outcome.
Okay, thank you for the answers.
Thank you. I have questions for Mr. Martin and Mr. Konopask, and if others want to add, please feel free. Mr. Martin, first let me ask Mr. Konopask. The airworthiness limitation instructions are part of instructions for continued airworthiness. And as part of that, it sets forth inspection intervals, including inspection intervals for principal structural elements, correct?
That is correct, yes.
Okay, and what year was it established that the FAA, I believe it was May 2nd, 2007 in the airworthiness directive, but established 19,900 cycles for the the aft bulkhead?
The 19,900 cycles, to the best of my understanding, was established at time of certification. The 2007 date that you're referencing addressed 4 separate principal structural elements, which the thresholds were adjusted based on criteria I'm not as familiar with.
Okay, what year on certification?
I believe that was 1990.
Okay, great. So any changes to airworthiness limitation instructions, and this is what I asked yesterday, Mr. Martin, are those major changes?
Yes.
And would it change, could it affect certification data depending on what the change is?
Yes.
Okay. So in 2014, Boeing submitted a certification plan to the FAA to increase some of the inspection thresholds for their airworthiness limitation instructions. And the proposed certification by analysis would have extended the threshold inspection for 104 MD-11 principal structural elements from 19,900 flight cycles to, it ended up to be 29,260. That was submitted to FAA for approval in October 2015. First, can I ask, as part of any sort of ALI or airworthiness limitation instructions or certification, would you consider fleet history or have fleet history in the documentation?
The certification engineers could ask for any service history when they're evaluating on the FAA side. It should be considered.
Mr. Fairhurst, you seem to be shaking your head. Do you want to add anything?
No, I was just nodding in agreement that whether it's an extension of an interval or a contraction of an interval, either way would be, after certification, it would be, should be in consideration of in-service performance.
Yeah, so, and that's what I want to ask about on in-service performance. So you have an extension on inspection of the aft bulkhead and the forward and aft lugs from 19,900 cycles to 29,260 cycles. I'm wondering what was submitted at that time for that approval what is submitted by Boeing?
So Boeing would be submitting the data necessary to justify the extension. In this case, as was discussed yesterday and a little bit today, Boeing demonstrated those higher thresholds during the original certification, but there was a initial threshold established by the Los Angeles FAA office of 19,900. So for the 2014 project, they would have come in, or they did come in and propose that the original certification data was still valid and the extension met the requirements.
So it would have been the information from 1990
Correct.
that was submitted for the 2014-2015 extension.
I believe so.
Was there an FAA approved that a month later, was there any submission by Boeing of in-service experience such as fractured races?
To my knowledge, there was no information like that. And if we had information that there was aft lug cracking, we would have more likely issued airworthiness directives to reduce the threshold, not escalate it.
Can I have 2 minutes? So at that time, because I'm looking at my chart, I think, and could somebody pull up 7Z? Sorry, Errol. Mr. Jordheim. Thank you. So at that time, FAA would have only had the 2007 and 2008 reports. But Boeing would have had a report from 2002, September 2007, August 2007, July 2008, October 2008, February 2009. So I'm wondering why Boeing wouldn't have, do we know, did you submit that to FAA, that information?
So the records that we've been able to review and the understanding that I have of the in-service fleet history associated with the certification project are firstly tied to the items defined as safety in our continued operational safety process. And then secondly, so the intent of the airworthiness limitation instructions is to identify fatigue cracking. And going back to, as I described the bulkhead assembly earlier, has a lot of similarities to the DC-10. And so based on the records that we have, the team reviewed the DC-10 and MD-10 history as well, which had performed their respective AOI instructions as a result of the airworthiness directive defined in 1980, every 20,000 flight hours. And so there was a number of records that were considered, the high time aircraft being, I think, just over 30,000 flight cycles at the time of submission for this airworthiness limitation instructions. And that was the data that was included in the certification package and presented to the FAA.
But do you think FAA should have had the information that you had fractured races in 1, 2, 3, 4, 5, 6 different times, you know, of right up until 2014, from 2002 to 2009, rather than looking at 1990 information? You think that should have been considered?
I believe transparency is critical in that process. I don't know what the engineers were considering or how they were considering, or if they considered those bearing failures in that discussion. I can't say.
Is it, does it have anything to do with you not considering those to be a cost event, except for one of them?
Again, I'm not sure.
It's speculating.
Yes, it would be.
Appreciate that. Okay, I'm going to come back to this. Thank you for giving me additional time. Certainly, if any of you need additional time to finish your line of questioning, please do. Vice Chairman Graham.
Thank you. Part 25 regulations require damage tolerance and fatigue evaluation of structures, and specifically 14 Code of Federal Regulations Part 25 decimal 571. There are 4 specific instances where an aircraft must be capable of successfully completing a flight during which a structural failure or damage occurs. These instances are bird strike, uncontained fan blade impact, uncontained engine failure, or an uncontained high-energy rotating machinery failure. So for the FAA, why does this regulation limit itself to these 4 specific instances?
I'm not sure that we've considered other types of events like that for this rule, but rotor burst is the I guess the first thing is bird strike is an event that occurs often. And so that is the requirement for the overall airplane for Part 25 airplanes for bird strike. And it's happens to be included in 25,571. And then rotor burst is another event that occurs in service. And so from a structural standpoint, the aircraft must be shown capable of withstanding that event. I'm not sure what other events could fall into that. I believe it's called, that section is called discrete source damage. So that's discrete events that cause damage to the airplane. And the requirement is that the airplane be capable of withstanding that and landing.
Are there any other instances of in-flight failures where the FAA deems that aircraft should be capable of completing a flight?
Well, there's many failures that, in general, that the aircraft is capable of withstanding. Not extreme ones like bird strike or rotor burst, but system failures, for example, individual flight control failures, many different failures that are covered by other regulations.
Okay. Would you say initial design evaluation and testing is the primary method of compliance with this regulation?
With 25,571E discrete source?
Yes.
So that's for the rotor burst requirements, it's an analysis evaluation to show that there's adequate structural capability. There's also the 25,901 requirements, I believe, that talk about minimizing the hazards to the airplane outside of structures. But for bird strike, it's test and analysis.
Okay. Thank you for that, Mr. Martin.
Sure.
For Boeing, does Boeing evaluate any structural failures beyond the 4 listed in Part 25.571 to ensure aircraft can complete the flight?
I will answer that. Thank you for the question. And I'll just add to Mr. Martin's comments, the discrete source damage requirements, which were added to 571, they weren't a limitation, they were an addition to make sure that those discrete events would be covered in the analysis and in the testing. With respect to what Boeing considers, there are many, many configurations that we look at that are beyond what's listed in the regulatory requirements. A simple example that I could provide would be if you consider a fuselage of the airplane, there's no requirement for a certain level of discontinuity in showing that capability. We, by our Boeing requirements, show what we call a 2-bay discontinuity. So between 3 frames that we show that discontinuity over those 2 bays with the central frame failed, and that we show that we would still have continuous safe flight and landing with that discontinuity. It's part of our internal robustness requirements. So that's just an example. There would be many examples of things we check to make sure we have robust structure.
Great. Thank you, Mr. Chisholm. That's all I have.
Member Chapman?
I have a couple other questions, but I think they're better for the next panel, so I will hold them for that round of questioning. Thanks.
Member DeLue?
Yeah, this really, I guess, really is for Boeing. So we've been talking a lot about the spherical bearing and any kind of previous reports. And Chairwoman Hominy, we just showed the graph again. But did you ever receive at Boeing, do you know, during the investigation, reports from operators about a failure or a fracture in one of the lugs, whether just the forward or aft lug? Not having to do with the bearing, just any issues with the lugs?
The only record, to my knowledge, would have been the one that was considered in 2007. I will preface that it's not uncommon for us to receive corrosion type findings, just general visual type items that wouldn't be associated with a similar type of defect.
So just that one report that you had with the lug, would that have been enough to give pause to think, which I know you can't answer for that, but would it have given the engineers a pause to think before they asked for the certification increase to 20,000? I mean, we're just talking just the one lug.
If that lug had been considered, there likely would have been more analysis to understand how that impacts the request for escalation.
Okay.
Obviously, there likely would have also been further analysis done previously, and yes.
Yeah, that was really my question. So not so much even with the bearing necessarily, just the lugs themselves, because you're requesting, since it's a principal structural element, all it would have taken just one event like that would have been paused potentially, right?
Yes, as part of the in-service fleet investigation, they would be considering reports such as that.
Great, thank you. Mr. Martin, appreciate the information on Part 25, but I do have a question about that piece. So you said in 2014, they increased the requirement that for a gear-up landing for a commercial aircraft, you added the 5 feet per second, which for most people, pilots, it's in feet per minute, so that's about 300 feet per minute, roughly. So a question just on the logic for my own benefit on that. I mean, if I was going to land a 787 with the gear up, it's probably going to be a very smooth landing, I would hope, about maybe 80 feet per minute, which is what I normally land at. But 300 foot per minute with a gear up, that seems like a pretty unusual thing, because that'd have to be a super worst case scenario, right?
Yes. And so that's by design. The requirements are built to be conservative. So that's a extreme event for sure.
So with that logic, then, if I had the gear come down, so I'm going to land gear up, we're probably going to grease it on the runway, hopefully a paved runway per your definition. With that case, we wouldn't expect the pylons to separate then, correct?
I wouldn't think so.
Okay.
For a smooth landing.
Well, because you showed this picture how it's going to land on the engines underneath the wing, but with the new design that you put in, a smooth landing, the pylons will not separate. They'll stay connected to the wing.
Right.
All right. Just all of us pilots would like to know that.
Yeah. But the rules don't speak to that.
Right. It has to be 5 feet per minute or greater.
Yep.
Okay, great. All right. Thank you very much. That's all my questions.
I just wanted, and again, I'm not sure I heard that correctly. Did you mention to Member DeLu only one that affected the aft lugs that you're aware of?
Yes, to the best of my knowledge, there's only one report of a crack in the aft lug as defined in the 2007 report.
And were you asking specifically, was he asking specifically about cracks?
That is how I heard the question. Apologies if I did not hear the full intent of that question.
Yeah, I don't think he specifically asked about cracks. So any impact on the aft lug?
Would need to be understood as part of the approach to the airworthiness limitation instructions.
Okay, can you pull up 7Z again? Okay, so I just want to review, we have July 2002, and we had a fractured pylon aft bulkhead spherical bearing outer race, which was reported to Boeing on July 10th, 2002. That failure occurred at 8,515 cycles. In the entire outer race of the spherical bearing was fractured in half, and the aft bulkhead forward lug was deformed forward with a measured gap of 0.032 inch between the laying surfaces of the forward and aft lugs as measured at the upper edges of the lugs. There was also wear damage in the forward lug. Also damage in the lug bore. Let's move on to August 2007. That was a fractured pylon aft bulkhead spherical bearing outer race, which was reported to FAA, and in the service difficulty report, that failure occurred at 8,663 cycles. September 2007, that was a spherical bearing outer race failure at 6,058 cycles. In that one, the entire outer race of the spherical bearing was fractured in half, and the forward and aft sections of the outer race had migrated out of the forward and aft lug bores. The upper edges of the forward and aft lugs were in contact with the wing clevis fitting. The maintenance contractor removed the aft half of the pylon aft bulkhead and reported in a crack in the aft lug near the I don't know what a fang surface is, but I'm going to go with that at the 9 o'clock position. Then July 2008, there was a swage flange, a staking ring separated aft staking ring at 9,765 cycles. In October 2008, there was an outer race fracture at 11,172 cycles. In February 2009, there was a spherical bearing outer race fracture at 13,650 cycles, and the contractor reported that the grease protruded from between the bulkhead lugs during lubrication, indicating fracture of the bearing outer race. And then I'll have to stop because in 2017, that was after the 2014, there was a deformation of the lugs. But my point is, you didn't even get to 19,900 cycles, but then you put in an application based on a change based on 1980s, barely 1990 data. Not you, I'm sorry, I don't mean you, Boeing. You all are being wonderful. I know it's hard to get tough questions, but thank you for your answers. But Boeing had put in an increase in inspection intervals from 19,900 to 29,260, and seemingly no one looked at these in-service failures. I don't understand that, because Boeing received not just the reports of the failures from 2002, 2007, well, 2 in 2007, 2 in 2008, 1 in 2009, but also there was a Boeing service letter in May 2008 and a revision to it, which prompted another Boeing service letter in February 2011, which should have been considered in the request when you're putting in an application to increase inspection intervals in October 2015, or at least providing that information to the regulator who must consider that. At the same time, I'm kind of wondering, if you're the regulator, why wouldn't, knowing that service letters are out there, knowing there were at least a couple of events that occurred with fractured races, I'm confused on why you wouldn't ask for more information, more testing, and why you would just accept information that Boeing provided in the late 80s during certification, 30 years earlier, basically. And I don't mean you, I meant entity. Can someone help me understand that? Because the application was October 2015, the approval was November 2015. That's only 30 days. That's pretty quick.
I think as was discussed yesterday, there was not an appreciation of the understanding how the bearing failure affected the stress in the lugs. And so part of it was the communication paths of the reports finding their way to the FAA, but the other part was, I think, collectively not understanding how the bearing failure manifested as a change in the
Yeah, because there were deformations of the lugs that were noted in some of these, so that definitely should have been considered. And I'm just thinking going forward, respectfully to Boeing, if you submit, 2 weeks from now an increase in an inspection interval, how does FAA know that they're getting all the right information? I mean, seems to me a decision was made based on some information, but not the full picture.
I'd say that's correct, not the full picture. When we're doing certification, we look at the data that the applicant is bringing to us. There should always be questions about what is the service history with this part or this area that we're escalating the inspections for. But it should be part of the data package, any service history that's out there.
Thank you, Mr. Martin. Again, I'm sorry, I'm over time. Take as much time as you want. Oh. Okay, I have a couple additional ones. Mr. Fairhurst, what's the difference between FAA approval versus FAA acceptance?
Yeah,
And to be fair, he was going to chime in earlier, but didn't know if he should raise his hand or not. So he had the answer.
Yeah, thanks for the opportunity to clarify. It was an action item that I don't think needs to be an action item. So at the time of certification, the applicant would establish, and working with the certifying office, establish airworthiness limitations. And so we've been focused a lot on the structural ones, but they're also equivalents for the systems on the aircraft. So those would be certification maintenance requirements. But between those intervals, required tasks and intervals are part of the type design and are approved at that time. There's also a requirement for instructions for continued airworthiness. So 25-1529 specifies that there must be ICA, instructions for continued airworthiness, provided so that once the certified aircraft goes into service, it can be maintained. And so the nuance is that the airworthiness limitations are approved by the FAA as part of the certification project and as part of the type design. But then the instructions for continued airworthiness are that we use the term accepted by the Flight Standards Organization that then continues to work with operators as they maintain their aircraft into service. So if there are changes to the instructions for continued airworthiness, that's not a certification approval, that's rather a flight standards continued management of the instruction for continued airworthiness with the operators.
Can something be unaccepted?
Right, I think I got to answer that. If there was an unsafe condition, we could write an airworthiness directive. If there were a change in, I think we're focusing right now on like intervals and practices, but if there's a change in those would be typically communicated by Boeing and then accepted. But if they were, really the only way to undo something is to write it if it was unsafe, and we wrote an airworthiness directive for it. But there are changes in both directions of for maintenance activity that are that if it's not an unsafe condition would be done outside of the realm of the certification office.
And the requirements now, after the accident, can you describe what's required now as a result of this accident for bringing the planes back into service?
Right, so airplane was grounded by an airworthiness directive and with undefined criteria for return to service. But now for the return to service, the bearing has been redesigned, and there are, I don't have the details on the intervals, but there are required intervals for inspection and replacement.
Yeah, 4,000 cycles, right? Question, for the PSC, for the extension from 19,900 cycles to 29,260, were those for the lugs, or what specific?
That STC package included, I think, 104 different items. So it would have just included, as part of that, the lugs.
Okay. The reason why I'm asking is now that you know you didn't have all the information from Boeing, does FAA plan to go back and take another look at that? And to see if those inspection intervals on everything else are adequate and ensure safety?
Well, I think we're basically starting from scratch now with the MD-11. So it was, like Ken said, it was grounded by airworthiness directive. And to get it back to flying, the FAA will review the Boeing proposal, which includes new bearings, new inspections, and new life limits. And so we're basically starting over.
Yeah, I just hope it's not just new life limits focused just on the bearing. You have to look at, I mean, you're going to have to look
Yes.
at all that
Sure.
damage to see if you have to go beyond just that bearing. And if you didn't receive a full picture of in-service flight experience, I hope you consider that. Thank you. I think we're going to recall Mr. Springer and Mr. Deckard. And I'm going to turn it back over to the technical panel for that.
Thank you. Chair, these witnesses were sworn in yesterday, and they remain under oath for the duration of the hearing. I think this question goes to Mr. Springer, but what is required? So let me start off with the inspections driven by the maintenance planning document, the 60-month inspections, detailed visual and general visual inspections. They started off at 60 months, and UPS now has them at 72 months. Is that correct?
Yes, that is correct. Both of those inspections are now at 72-month interval.
And what is required for, who approves that extension?
As a Part 121 operator, we have an approved reliability program, and we have a detailed process and procedures in our aircraft reliability program manual to make adjustments to our maintenance program. Specifically talking about these two tasks, in 2015, we made an overall adjustment to our C-check interval from 15 months to 24 months. So as part of that process, we take a sampling of multiple C-check data for all the cards, and I'll talk specifically to these two cards. So there's a sampling across an age of aircraft to gather the data to see what findings that had been identified under the 60-month interval. That data was analyzed. We actually used a consultant that helped us analyze all of our data when we did this significant change to the entire program. So once the data was analyzed and there was no adverse trends noted with the findings at 60 months, then we had to realign it to the 24-month interval. The adjustment was made. That overall package was submitted and approved by the FAA, our Certificate Management Office.
Okay, and with this data set that you have to give to the FAA to prove that it's safe to extend from 60 months to 72 months, you mentioned you take a sampling of your fleet. Just do you know ballpark about how many aircraft that would be? Talking 2, 3, a dozen?
It was, I'd seen the package. It was more in the area of a dozen in that sampling. We could get the details. Part of the adjustment from 15 months to 24 months was based upon our utilization, because we had a low utilization. And what I mean by utilization is the number of hours or cycles that we fly a year. Our hour utilization was relatively low, and that's what led to in 2015 to looking at this adjustment. And we were following, typical industry practices for an adjustment to a program.
All right. Thank you, Mr. Springer. And I actually don't have questions for Mr. Deckard. So this question goes to Mr. Konopask. So with the airworthiness limitation instruction increase that was in 2014 to 2015, the data used to justify that extension from the 19,900 cycles to we'll say close to 21,300 cycles, that was based on the original certification testing of the Pylon, correct?
To clarify, it's the extension from 19,900 to 29,200.
Yes, sorry about that.
That is from the original fatigue analysis. That threshold would have been calculated from that number.
Okay, and with that original fatigue analysis, is that analogous or data obtained from the Pylon testing you talked about when it was done as an assembly up to, I think you said 2.5 times?
The testing was performed separately. The fatigue testing or the data that informed that threshold was a compilation of the external and internal loads of the structure, and then a fatigue spectrum created, and then that life calculated.
And given that the ALI increase was requested, let's say about 25 years after, about 25 years after original certification, what team does the certification project for the ALI increase, and is that separate from the team that does service engineering reports and cost reports?
With respect to the team construct at that time, I'm sorry, I'm just unaware.
In today's practice, if Boeing were to request an airworthiness limitation increase similar to this one, would that team pull data from service engineering, from cost, to get an idea of the in-service experience prior to requesting a ALI increase?
Yes.
Can you talk to me about what other data sets that they might look at besides costs and in-service reports before submitting the package to the FAA for approval?
The two main areas that they would review are, as you mentioned, the continued operational safety data, the other data set, which is, we discussed quite a bit yesterday, is the Boeing communication system that contains a lot of detailed information. The insights that are obtained from being able to engage with operators through the Boeing communication system are extremely helpful in understanding the origin of the damage that's reporting. And I think that's a really important element when you're looking at any sort of change to the aircraft, and in taking into account fleet history, is ensuring that you understand the context of that data. And so because we are working together with operators through that channel, usually we have a lot more context there.
Thank you. And when the testing was done with the Pylon assembly, there was no damage that was readily observable of the bearing. But in service, we've got history where we've got various bearing failures before the 19.9 of the original limit. And so should that have informed the ALI, whether or not an ALI increase was appropriate? That in-service history that showed the cycles for the bearing failure was lower than what was shown from the original testing of the pylon assembly?
I can't speak to what information they had at 2015 or how they were considering it. Again, as we've spoken about, the understanding of how the bearing fracture impacts the lugs now is significantly better understood after the accident. It was not intuitive back then. And furthermore, as I've briefly mentioned in my past statement, the context matters. And so I think, again, I don't know if they considered or looked at the bearing failures previously. They likely would have, if they did, understood or tried to understand the origin of those failures or origin of the impact on the lugs, whether that's from the interference fit of the bearing itself or something else associated with the lugs. But again, I don't have that information.
Thank you. And for the FAA, when you receive a ALI increase, a certification project like this where a applicant is looking to increase the life or the cycles for a airworthiness limitation, is it required for the applicant to show in-service history if there is substantial in-service history for that part?
Yes, it's required by to show compliance with 25,571. That would have to be taken into account.
Okay. And does the FAA rely upon the applicant to provide all that information, or does the FAA also do independent research per se, like looking through SDR reports and whatnot for the part?
We rely on the applicant.
In the lens of this accident, or after this accident, and understanding some of the factors we know so far, we have a pretty good picture with the story with the aft pylon, the pylon aft bulkhead. Given that there is, potential other issues that are in service, such as the other PSEs, is that something that the FAA would reconsider or look at further with this ALI increase? In a sense, we have one part here that the in-service history might not have been considered with the pylon aft mount bulkhead and the bearing, but for the thrust link, for the forward bulkhead, for other PSEs on this pylon assembly, would something like this accident and the understanding we have so far with it drive the FAA to do a review of the whole ALI increase, or the ALI increase as a whole?
I don't know if that's something that we are undertaking right now. It would probably be a good idea to look at what was done. I know we have been doing that ever since the accident to try to understand what was done and why it was approved. But I don't know exactly what the current review consists of. I want to go back to my previous answer when I said we rely on the applicant. I didn't want to imply that we just take the data and decide yes or no. We rely on the applicant, but we will usually go back to the applicant, and there's a lots of discussion about the details, but we don't typically go do our own research for these kinds of projects.
Does the certification office, do they pull principal inspectors of operators of this type for their experience, what they've seen, if they have any concerns with an ALI increase?
No, not usually.
Would that be a good practice, in your opinion?
If it was something significant and we felt like there wasn't enough information coming from the applicant, but I haven't heard of that kind of a survey being done by the FAA of maintenance records to evaluate a proposal from an applicant. The responsibility is on the applicant to substantiate their proposal.
Do you know, are principal inspectors notified when there's an application for an increase like this?
Yeah, no, that would not be typical.
All right, thank you. Chairwoman Hamidi, that's the tech panel's follow-up.
Oh.
Can I ask one question and follow up? Boeing, today, would you look at SDRs as part, when you're considering submitting an application for an AL, for any sort of an inspection increase?
I'm unable to answer that. It's just not my area of expertise.
Okay. And FAA, you wouldn't normally check the SDR database just to see, double check?
Yeah, I think as discussed yesterday, our best source of reports are through the applicant, through Boeing, in that they've got the best communication and the best write-ups of their cost reports and in-service history.
The problem is if they only considered one out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 events to not be COSP, that's a problem.
Right, and we discussed there was a misunderstanding of or lack of appreciation of the impact of the bearing failure on the lugs. Regarding if I may, regarding the question about other installations or other ALIs, by process, Boeing, when they have assess something through their safety review board like this, lug failure would have gone, by process, and they can maybe talk to it, but they go through and look at other models and other installations. So it's a natural, it's something that we expect them to do and that they do themselves according to their standard practices. And then also, I think I don't want to lose sight that we do have a robust cost process as far as receiving reports. And if you look at the Federal Register, we write a lot of ADs about structural issues where there's fatigue occurring, and the existing inspections are unacceptable, and we write ADs to go after that. So I think we've got an instance here where we collectively didn't understand the effect, the higher level effect of the bearing failures and how they were affecting the stress. But we do have, I don't want to leave you with the impression that the FAA doesn't have a system of receiving reports, investigating reports, and taking action and writing ADs. That's what we're doing all the time.
Thank you. I would just hope that, as Mr. Shin had questioned at the end, that that FAA does take a careful look at what was approved for those 104 different changes and inspection intervals, because if you had only part of the information for this, I'm just wondering if you had the full in-service history for other principal structural elements.
Great.
Member DeLue?
Yeah, I'd like to just follow up for clarification, Mr. Fairhurst. So in the same case here, when you're looking for an increase in inspection cycles or so, did I understand that your office, the FAA, you do not consult nor call the CMO of a major airline? You don't talk to the POI, the PMI, the PAI, you don't even discuss it with them?
I maybe should say I don't know exactly what the office does. It would be rare for us to talk to the individual CMOs. We do have an interface to the Flight Standards Organization through our Aircraft Evaluation Division, and so it may be that we consult with them. I should halt there because I don't work in this structures area.
No, I get that, but for something important like an increase or something like that, I mean, we would hope, I'm pretty sure that's the case, where a CMO is fairly engaged with an airline or major operator. But the fact that you're saying the office that's looking at it wouldn't necessarily talk to those folks, these principal inspectors or the POI or PMI, I find that somewhat surprising if that is in fact the case.
We do talk to the CMOs about it, but it's mostly about in-service issues rather than life extensions. And I would also say that life extension programs are fairly rare.
I would just propose that the CMO's office has the availability of ASAP reports, and they've got their finger on the pulse of a particular operator. So thank you for your clarification.
Good. Technical panel, anything further? All right, just want to make sure parties have an opportunity. One more time, Boeing,
Thank you, Chair. No questions.
FAA,
No questions, thank you.
Teamsters,
No questions.
STE, San Antonio,
No questions.
UPS.
Yes, we have some questions. I'd like to follow along with your line of questioning, Madam Chair. Could we have Exhibit 7Z brought up? So looking at 7Z, the February 2009 Operator 3, if I want to paraphrase this, but if we go, we don't need to pull it up, but the structures report on page 57 establishes for that particular event right there that Boeing knew that you could have bearing damage, but no migration. Mr. Hirsch's testimony yesterday that to Boeing's knowledge that there was always migration when the bearing was damaged was wrong. Isn't that correct? And that question is to Boeing.
To clarify, I don't recall specifically what Mr. Hirsch stated, but I'll just speak to this installation itself. And it's hard to discern what type of damage is physically here. I believe the terms that I used was if the bearing has a radial fracture around the entire circumference of the outer race, it would be expected that the bearing migration would occur shortly thereafter. The interference fit of that bearing wouldn't necessarily be enough to retain it, and the staking feature would no longer be applicable because it is fractured around the entirety of the surface.
But you could have cracks without separation.
That is correct, yes.
Some other questions for Boeing. You mentioned that you didn't understand, you said you didn't understand the effect of bearing failure and lug deformation damage, but you knew that both were occurring. Did you, prior to the accident, ever do any analysis on the effect? And if not, why?
Can I ask you to re-clarify the question different way? Apologies, I'm just not sure I'm able to answer it as it's phrased.
No, so we had both lug deformation and damage and bearing failure occurring. So you knew both of those events were occurring. So prior to the accident, did you ever take an analysis of that entire event, both of those things happening, rather than just looking at one item, spherical bearing, or just the lugs, but the combination of that?
So I don't know what information the engineers had or how they were considering the two together. I don't know what communications took place outside of the Boeing communication system with those operators to better understand it. I mentioned before an interference fit in the bearing, and I mentioned a production gap that was also associated with the assembly. And so how those factors were considered in trying to understand the relation between the two, I just don't know.
Okay, one other question. I want to go back to the ALI, and we've talked a lot today about the threshold for the lugs at 19,900, escalating those up to the 29,000, I think 260. But after the accident, the limitation is now every 450 flight cycles. So it's a significant change from the 29,000 down to 450. So what was the difference in the analysis of the lugs for that change?
To support the return to service of these aircraft, we put a lot of effort to make sure that we understood the situation in its entirety in close collaboration with operators. And as part of that, there are many circumstances which we take very conservative approaches to make sure that we're able to support the respective operations of the operators. So I can't speak to necessarily the exact stress state as it relates to what might have been on the aircraft at the time of the accident versus what the return to service approach is, because the two are not directly correlated and there's still a lot of investigation going on there.
Thank you. No further questions.
Okay, we're going to take a 50. Oh, you have a question?
Thank you, Madam Chair. Just a question. Clarifying, because I don't believe, and if you could confirm, we don't have a transcript available from yesterday's proceedings, correct?
Mr. Shin, go ahead. No, we do
don't
not
have
yet.
one yet. We will provide it to the parties in 7 days.
Thank you very much. And so perhaps in the absence of a transcript, carefulness around characterizing the words of what others said yesterday.
Sorry?
We would urge caution for our party to characterize a witness's testimony as wrong. We don't have any further questions beyond that, but just we think that there's a characterization of Mr. Hirsch's testimony yesterday that was not correct.
Okay, I don't think we understand what you are, the point.
Perhaps we can handle this offline at the break. I think that what I'll say is I think that we believe that there was a mischaracterization of Mr. Hirsch's testimony that predicated one of the questions that was asked.
Understand. I think Mr. Shin can get together with you and you can discuss that. Okay, great. Any other questions? All righty. We're going to take a 15-minute break. We'll be back at 11:15 and then we'll start the second issue area. Okay, thank you. We're going to move on to the second topic with Mr. Shin in just a second. I just want to take a moment to remind everyone that this is an investigation and we are in the fact-finding phase. This is a part. This hearing is a part of that fact-finding. We do not have adverse parties. We are not here to determine legal liability and or cross-examine witnesses. So if you want to question a witness, I would not categorize a witness's statement who's not here right now as wrong. I don't think that's appropriate. And so, you know, if we want to ask a factual question on what was said or ask for an expansion, I think that's okay. But no cross-examining witnesses. Okay. With that, Mr. Shin.
Thank you. This section will focus on the design of aircraft systems routed through and near pylon attachment points, such as fuel and hydraulic and electrical lines, including the vulnerability of these systems during pylon separation failure modes. The witnesses remain under oath, and the witnesses and technical panel members remain the same. I will now hand it over to Mr. Wagner.
Thank you. As we begin, I just want to kind of chart the course for this round of questioning. So in the previous round, Mr. Cruikshanks and Ms. Oki established some requirements for gear-up landing, which McDonnell Douglas took and designed these fuse points into the engine for that condition. So now that we've established that, we're going to be discussing in the event of a pylon fusing event or separation, we want to understand what the effects of that are on the aircraft systems. So we're going to be breaking that into two sections. First, we'll be focusing on FAA requirements, and then we'll be looking at Boeing's design. So let's start first with a question for Boeing. What safety critical systems are routed through or near the wing engine pylon on the MD-11?
Thank you for the question, Mr. Wagner. Perhaps it would be useful to bring up Exhibit 9A. I believe it's page 15, figure 9. This is from the systems factual report. Yes. So I can talk through what's labeled here that very accurately describes the systems in the vicinity of the pylon. What we see here is a top-down view with a cover panel removed. So starting in the upper right-hand corner, you see fire detection loop A and B wiring. Below that, there's a label that says slat extension and retraction hydraulic lines. We do have a pneumatic system in this area. And then the pipe in the middle of the photo is a fuel pipe. And then we see power feeder cables down near the bottom. Progress to the lower left-hand corner. There's a label that says pulley and cable for L3 slat. There is one non-systems component labeled here that says forward pylon to wing mount, and Mr. Konopask described that forward engine mount. That is that structure shown from above. And these pictures are from an exemplar airplane during the investigation. And then engine 1 fire shutoff valve wiring. I think it's hard to see the wiring, but it runs through that area. And then the L4 slat proximity sensor wiring.
Thank you. So over to the FAA. What are the certification requirements for safety critical systems?
So as an example of some different requirements that would apply in that area, there's 25863, which requires the minimization of the probability of ignition of flammable fluid and a crew alert if crew action is required. 251189G requires that the shutoff valve not be affected by an engine mount failure. There are also separation requirements due to rotor burst and system safety requirements, flight control requirements, et cetera, that would apply.
Okay. So we previously mentioned the requirements in Part 25, 721, 963, 994 that mention that an engine separation event should not lead to fuel spillage. How does the FAA define fuel spillage?
First, I want to add to my previous list, 25994, wheels up landing does require an assessment of fuel systems. In the final rule for 25, the most recent amendment of 25994, 25721, and other rules that was done in 2014, we had a comment question about what is the amount of fuel that is considered hazardous. The rule says the amount of fuel that would constitute a fire hazard. So that was a question we got to the proposed rulemaking. And in the final rule, we pointed to a previous special condition that had to do with tire debris, where we did define it in the special condition as a running leak or a dripping leak. So a pretty small amount, but it's stated there in the final rule of those requirements.
Is the small amount of fuel quantified in any documentation?
No.
Okay. Does the FAA consider fuel spillage to apply to both breached fuel tanks as well as broken fuel lines?
Yes. Specifically for 25994. 25721 is focused on fuel tank rupture, but I don't think it's technically specific to that. It just talks about the amount of fuel. Doesn't say where it's coming from.
Okay, thank you. Mr. Jordheim, please pull up Exhibit 9C, page 10, that shows the current version of 14 CFR 25.1189G. This was previously mentioned by Mr. Martin. It's short, so I'll just read it. Each tank to engine shutoff valve must be located so that the operation of the valve will not be affected by power plant or engine mount structural failure. How does the FAA define engine mount in this context?
Engine mounts would be considered all the attachment structure from the wing to the pylon itself, and the pylon to the engines. When we look at this regulation and what is meant by engine mount failure, we found that the regulation 25994, wheels up landing, was introduced at the same time that this regulation was introduced. So we believe that although there's nothing stated in the proposal or the final rule, we believe that the intent of this rule is to address the potential for engine mount failure in a gear up landing, wheels up landing.
I want to ask this to Boeing. What is Boeing's understanding of engine mount in this context?
Thank you for the question. For this context where it is about the protection of the fuel shutoff valve in 1189, it is actually immaterial as to whether it would be the engine mounts. Colloquially, we often think of the engine mounts being the mount of the engine to its support structure. But whether it's the engine mounts to the pylon or the pylon to the wing, in this case, it wouldn't matter. The assessment that was done for the protection of the fuel shutoff valve would apply to either scenario.
Okay, thank you. Back to the FAA. Does this regulation, 1189 Gulf, apply to the location of the wiring for the valve, if it's an electrically controlled valve, as is in the MD-11, or just to the valve itself?
Yeah, I think the intent is that the valve would be able to function. So therefore it would apply to the wiring as well.
And one more question about this regulation. During which phases of flight does this regulation apply? Or what was the intent, I guess, at the time of writing this regulation?
Or to clarify, you're focusing on 1189G?
Yes, sir.
Yeah, so that would be, while it's generic to engine mount structural failure, the only scenario laid out would be engine mount structural failures regarding landing scenarios.
All landing scenarios, would that include both a gear up scenario and a hard landing scenario?
Right, as per 721.
Okay, thank you. Mr. Salji will take it from here.
All right, thank you. I have a couple questions. First to the FAA. Mr. Jortheim, if you could pull up Exhibit 9 Alpha, page 16, and then zoom in on Figure 9, the figure we had up earlier. So the question to the FAA here, does the FAA require the aircraft systems routed near the wing pylons to be designed such that critical functions are maintained after a pylon separation?
No.
So why is that?
Because we design, we ensure that there will not be a pylon separation. We use the structural requirements to ensure that pylon separation will not occur. The only case where we do assume pylon separation is for hard landing events, off runway events, et cetera, per the rules. And in that case, the only requirement is around fuel spillage.
So just to clarify, even during scenarios, hard landing or gear up landing, the only system that's considered for this engine mount to be removed, the only system considered is the fuel spillage requirements and no other systems?
Correct.
Okay, thank you. Move on to some questions for Boeing regarding the fuel system. Would Boeing expect fuel lines to open during a gear up landing of an MD-11?
It is possible that we could have disruption of the fuel line in a wheels up landing. We saw the view earlier. Mr. Konopask showed a figure that showed the rotation of the pylon with a wheels up landing. It is possible that that fuel line could be disrupted.
So how did McDonnell Douglas show compliance to the fuel spillage requirements in Part 25, 561 and 721?
Okay, thank you. The requirements for the systems, and in this case, we'll focus on the fuel line in the center of the figure there, very similar to the requirements for the structural attachments, where we do not want when we have the disruption of the pylon, we do not want to breach the wing fuel tank. So that's the first requirement. The second requirement, in accordance with 1189, is to be sure that the fuel shutoff valve will not be disturbed. You cannot see the fuel shutoff valve in this figure. It would be off to the right. It's inboard of the pylon in this view, and it's toward the upper portion of the front spar. It actually sits just forward of the front spar, several inches forward of the front spar. And actually during the MD-11 development, the FAA inquired about this very issue and asked whether we had protected that structure in the event of a wheels-up landing. And we provided detailed structural analysis that showed that the valve structure itself, not only based on its location, but the strength of that structure, the housing that supports that valve, and then the strength of the spar web behind it were all significantly greater than the strength of the tube. Essentially another form of a structural fuse, but in this case with the fuel tube.
All right, thank you. Mr. Dortheim, if you could pull up Exhibit 9 Bravo and then PDF page 2. We have a simplified diagram here of the fuel shutoff valve location and the wire routing. So this question to Boeing, what was the design intent behind routing the electrical wiring for the fire shutoff valve in between the pylon and the lower wing skin?
Okay. Let me explain kind of the history of this wiring, because it did change on the MD-11 as compared to the DC-10, and for a very deliberate reason. On the DC-10, the fuel shutoff valve was a pulley and a cable system along the leading edge of the wing. So it went from the side of body of fuselage along the leading edge to that same location of the fuel shutoff valve. Yesterday, there was mention of in-service accidents. One of those was on a DC-10 was Sioux City in 1989. That did not involve a wing-mounted engine. It involved the tail engine. One of the recommendations that came out of that investigation was to keenly assess the rotor burst trajectory for uncontained engine fragments. So during the development of the MD-11, an assessment was done for engines 1 and 3, the wing-mounted engines, to understand those trajectories. And that cable that would operate the fire shutoff valve was within that trajectory. So the reason why we have this routing of the wiring, it goes along the rear spar in the trailing edge cavity, and then is underneath the pylon fairing structure, and then goes out to the fuel shutoff valve, is to avoid that rotor burst trajectory.
All right, thank you. And I think we established in a prior question that there are specific scenarios where an engine pylon is supposed to separate from the airplane during those landing scenarios. So would Boeing expect that the electrical wiring to the fire shutoff valve be compromised in those landing events?
No, we would not. I believe the two scenarios were shown earlier today. For the engine down movement in a hard landing, the separation is actually at the forward mount of the engine to the pylon. So obviously this area is not disturbed. And for the wheels up landing, we have a rotation around this area and this wiring would not be disturbed.
So those are the protections to make sure that the electrical wiring isn't compromised in those scenarios?
Correct.
Okay. Was any sort of analysis done to verify that, or is it kind of more of like an empirical thing? How did you kind of come to that conclusion?
So I have to clarify that I wasn't there to come to that conclusion. I would assume this would be a drawing review to understand that this area would not be affected just as I described.
Okay, thank you. So I think we'll turn it back over to Mr. Wagner.
Okay, Mr. Jordheim, please pull up Exhibit 9C, page 17, that shows the historical version of 14 CFR 251189 Gulf. So this is the version that was applicable during MD-11 certification. The question is to Boeing, how did McDonnell Douglas show compliance with this regulation at the time of certification?
As I mentioned earlier, the FAA inquired about this during the development and asked how the fire shutoff valve was being protected. And that was the detailed structural analysis of that installation.
I just want to be really clear about one question. So we've talked before about the event of a gear up landing and how the engine would pivot and rotate. And I believe you stated that in that condition, you would expect no collateral damage to the wiring that would control the fire shutoff valve. I know that complete pylon separation isn't a design consideration based on previous testimony. However, would Boeing predict that wiring be compromised during a more complete separation event?
So you're correct for the two considerations that were in view, a wheels up landing and a hard landing. We do not expect any collateral damage of that wiring. For another scenario that wasn't considered, if the pylon completely separated from the wing, it's clear from the figure we were looking at earlier where the wiring is attached within the aft portion of the pylon, that it would be disturbed.
Thank you. I want to turn briefly to the FAA in regards to this regulation, 1189 Gulf. Did the FAA retain approval or was it delegated to a designated engineering representative at the time of certification?
I do not know that. That would be from the time of certification. That would have been established as part of the certification plan, and that would be captured in an artifact in the files.
Could you take that as an IOU to present that information?
Yeah, we'll try to find that.
Thank you. I imagine that documentation would also answer my next question. How did the FAA find compliance between McDonnell Douglas's design of the wing fire shutoff valves and Part 1189? Will that also be part of the IOU, Mr. Fairhurst?
Yeah, that's correct. That would be the applicant has a responsibility to show compliance to the regulation, and then the FAA finds compliance. So it would be important to have that artifact or the deliverable where that was discussed.
Okay, thank you. Mr. Jordheim, please pull up Exhibit 9 Charlie, page 13. This exhibit contains an excerpt from Advisory Circular 25.994-1, paragraph 4 Bravo. Did McDonnell Douglas follow the guidance of this AC advisory circular when designing the MD-11's fire shutoff valve? Do you have record of that, Boeing?
To the best of my knowledge, yes.
What redundancy, if any, does the current design of the fire shutoff valve and its associated electrical wire routing have if either the valve itself does not function, it has a fault for some reason, or there's an issue with the wires that control it, such as a severed or a shorted wire.
So first, let me answer for the entire system. For fuel shutoff, there is inherent redundancy when the engine is attached. So there's the fire shutoff valve, which is operated by the fire handle. And there's also the engine control valve, which is operated by a fuel switch. Both of those are in the flight deck. So both of those will serve to flow the stem the flow of fuel. With respect to the operation of the fire valve itself, it is a single wire that operates that.
Okay, so in the event of a fault of that system, I guess barring a pylon separation, the crew would still be able to reduce the flow of fuel by using the fuel switches, you're saying. Is that correct?
Correct.
Okay, thank you. Okay, so in a scenario where an engine separates, would moving that fuel switch affect fuel flow to the engine?
With complete, I want to clarify, is the scenario a complete separation of the engine from the aircraft?
Yes, in this hypothetical scenario, we've got an engine and pylon that had separated from the aircraft. And I'm just wondering what the effect of moving that fuel switch would be.
That would have no effect.
Okay. And then pulling the fire handle would also have no effect. Is that correct?
In the hypothetical scenario that you described, with a complete pylon separation, not just an engine separation, which, as we discussed earlier, would disrupt the wiring to the fuel shutoff valve, then the fuel shutoff valve would remain in its last commanded position.
Okay, thank you. So I asked in that hypothetical scenario about the effects of those two control means. Just continuing that scenario, would the crew have any other way of mitigating or minimizing fuel flow to the separated engine?
No.
Okay, thank you. So I want to understand a little bit about the fire handles themselves and how they work. Do those fire handles provide any inputs into components of the fuel system upstream of the fire shutoff valve?
So I will share what I know. I am not an expert in all aspects of our fire shutoff valves. My understanding is first of all, just for context, the fire shutoff valves are located in the flight deck between the two pilots. And
excuse me, you mean the fire handles? Is that correct?
Sorry, yes, the fire handles that would actuate the fire shutoff valves. When the fire shutoff valve is pulled, there are two things that happen. One is the flow of fuel because of the closure of the fire shutoff valve will be stopped. It also isolates the hydraulic system that's associated with that engine.
Okay, so to your knowledge, and we can confirm this afterwards, but there's no input sent to the fuel system controller or modifying any pumps output.
The engine controller is controlled, by my understanding, by the fuel shutoff switch, which is a separate.
Yeah, I don't mean the engine controller. I mean the fuel system controller.
Not to my knowledge.
Okay, thank you. Do you happen to know, was Was this a consideration during the design of the MD-11 fuel system?
I can't speak to what was considered.
Okay, thank you. Mr. Salji will continue.
Got some additional questions for Boeing here on the hydraulic system. So based on the current design of the MD-11, what are the effects of a pylon separation on the flight controls of the MD-11?
Perhaps we could pull up figure 9 again from Exhibit 9A. You see in the upper right-hand area, it says slat extension and retraction hydraulic lines, and it's pointing to some hydraulic lines that run through the pylon structure there. If there were a complete separation of the pylon from the wing, obviously those lines would be disrupted, so that they would no longer be active.
What about in a partial separation in our 2 landing scenarios?
I can't speak to whether they would be significantly damaged. There's a slight rotation in this area, but I'm not sure that they would be significantly damaged. I can't say they would not be.
So are you able to speak to at all how the partial separation would impact the flight controls? Any control surfaces on the airplane?
For the ground condition that we're talking about.
Correct, yeah.
Okay, so I can give you the scenario of what would happen if they were completely disrupted. Again, we're talking about a ground condition, but I can speak to design features we have in place to address hydraulic system failures in general, and specifically for the leading edge slats. This actually goes back to another accident that was mentioned yesterday, 1979 Chicago. And in that one, that was the in-flight separation of an engine on a DC-10 for completely different reasons. But one of the issues that was raised and a recommendation that was made was to prevent the inadvertent retraction of the slats with the loss of hydraulics. So all the hydraulic lines on the leading edge of the MD-11 do have what we call slat balance relief valves, essentially a fuse, that if we lose hydraulics for any reason, that pressure will be maintained and the airflow won't push the slats back, so they remain extended.
Okay, thank you. So what are some other consequences if those hydraulic lines are severed during a partial or full separation of the wing pylon?
Certainly, hydraulic fluid is a flammable fluid, so that it would be one other potential hazard.
What are some of the effects of losing system pressure, both in one hydraulic system or in a dual hydraulic system loss? What would be some of the consequences if we lost hydraulic pressure in 1 or 2 systems?
That's a difficult question to answer across the entirety of all systems. It would matter which systems and which functions are affected. I did describe a moment ago about the changes we made for the leading edge slats to address the inadvertent retraction of those and the loss of hydraulic capability. All hydraulic systems are redundant. So we have 3 systems on the MD-11. Systems 1 and 3 run through both the left wing and right wing. And system 2 runs to the rear engine. In the event that we lost both system 1 and 3, we have some reduced functionality, but the airplane is still able to be flown.
All right, yeah, and I think we, if we can pull up Exhibit 9 Alpha, PDF page 49, and then zoom in on figure 41, you can kind of see a little bit of a schematic of the hydraulic lines around the wing pylon. So in the schematic, right, we see that there are hydraulic lines, and we saw in the picture that was up prior that there are hydraulic lines of two systems routed near the pylon. So some pylon separation can sever these lines or disturb these lines. And there can be a situation where there's a dual hydraulic system loss. How is this condition considered during the pylon design?
So as I mentioned, we do have redundancy of our hydraulic systems. So we can have a loss of both hydraulic system 1 and hydraulic system 3 and continue to fly the airplane.
Okay, so I'm not sure if you can speak to this. I think we kind of touched on this earlier. Was there any analysis that you're aware of that was done as part of this design for the hydraulic lines? Anything written down or anything that was certified to or looked at as a certification artifact?
Well, I'm certain there is analysis and there are artifacts. I'm not aware of the specifics, and it would be broad and far-ranging, dealing with many conditions and operations. If there's something specific that you'd like more information on, I'm certain we can get that for you.
Yeah, I think if we can write this down on our list of IOUs of just what analyses were done for the hydraulic line routing through the pylon and making sure that those lines wouldn't be affected by a pylon separation, partial separation, I think that would be good for us to have.
So for the wheels up or hard landing conditions?
Right, any analysis that was done on that.
Certainly.
And then Mr. Dortheim, in the same exhibit, can we scroll to page 79, please? And zoom in on figure 75. So this is a schematic kind of what the three different hydraulic systems drive, so to speak, on the MD-11. Sorry, it's a little bit difficult to read on the screen. So in a dual hydraulic loss scenario, whereas we lose system 1 and system 3, what would be the effect on the braking system of the MD-11?
Yeah, I would not like to speculate. We can get you that information.
Okay, thank you. All right, I'm going to pivot just a little bit. These questions are still for Boeing, and maybe the FAA may have something to chime in on as well. Can you speak to the process of modifying the design of an out-of-production aircraft?
Yeah, so an applicant would approach the FAA with a proposal. They submit a certification plan laying out their proposed changes and how they intend to show compliance to the regulations. And then with the certification plan would be coordinated with the FAA. And once that was kind of locked in as far as a path to approval, then the applicant would go and do all of the activities established in the cert plan, submit them to the FAA for the FAA's approval.
And what are some ballpark timelines as far as if they're making a minor modification versus a major modification?
They're all over the place. There's no set timeline for getting these done. There's for a change it's really about the scope of the change. So if it's a small change in a small area with few impacts, then it might be a fairly faster process. But if the scope of the change is larger and affects other systems and requires consideration of more collateral impacts. The airplanes are very integrated. So if you're affecting one area, it would be possibly affecting something else. And so needing to make sure that all those considerations are, considered and accounted for.
All right. And then I'd like to just ask one more question on the SLAT system. Just go back to that for a second. So as we saw in the systems group chairman's factual report, the SLAT proximity sensor wiring is routed near the engine pylon. During our investigation, the systems group demonstrated on an exemplar airplane that damage to this wire would lead to a SLAT disagree state. Do you know, this is a question to Boeing, would the SLAT disagree state affect the computed stall speed of the airplane in the airplane system?
My understanding is that with that sensor loss, that it is indicated the same as with slats retracted. And so essentially that's a smaller wing. We don't have the leading edge slats out, and that would affect the indicated stall speed.
Okay, and then do you know if that the effect on that indicated stall speed, would that have any effect on the function of the stick shaker?
I believe it would.
All right, thank you for that. Mr. Wagner?
Okay, for the last line of questions, we want to focus just briefly on crew indications. These questions are to Boeing, and so we're going to start with another hypothetical. In the case of a pylon separation, what are Boeing's expected flight deck effects to see during that event?
I would like to clarify, do you mean pylon separation in flight?
Yes.
So for that example, I won't make you go back to the figure, but in the figure it was clear that we have several systems that are routed through and attached to the pylon. At the top of the figure, you may recall there were there was an indication of two wires for fire loop A and B, and simultaneous disconnect of those fire detection systems would result in an indication of a fire. So the so you can see it here. Thank you, at the top of the picture, fire detection loop A and B wiring. So simultaneous disconnect of that would result in the same flight deck effects as the indication of a fire. And the way that would be presented to the flight crew is there is an oral warning, a visual indication, and a lighting of the fire handle and the fuel shut-off switch. Unless it's in the takeoff phase, if the airplane is less than 400 feet off the ground or within the first 25 seconds of flight, the visual indication on the flight deck and the oral warning are inhibited.
What would the expected effect be on the engine instruments on the display?
I'd have to get back to you on that, Mr. Wagner. I'm not sure.
Okay. So would an engine failure produce a similar indication on the display? Could you provide that, I guess, in writing as an IOU? Basically, in the event of a pylon separation, what would the engine instruments appear? And in the event of an engine failure, but a non-separating event, what would that appear like on the engine instruments?
Certainly, and we may have to clarify, we can do that after, what types of failures we should consider.
Okay. Okay, one clarification as well regarding the design philosophy. So we know that McDonnell Douglas designed the aircraft for potential gear up landing for the engines to pivot with the failure of the aft lug. In the other condition, emergency landing condition of a hard landing, is the pylon intended to fully separate in that case or just pivot as well?
So no, in fact, as Mr. Konopask showed earlier, the disconnect at the engine is actually between the engine and the pylon. The pylon remains in place. And so that's for a hard landing condition, which at that time was not part of the regulations, but it was part of the design consideration.
Okay. And what flight deck effects would you expect in that case, in a hard landing event?
I hadn't thought through that, Mr. Wagner. We can get back to you on that.
Okay, thank you. One last question for me. What are the expected flight deck effects of a wing fire with a pylon separation?
Can you clarify what and where you mean by wing fire? We do have fire zones, and then we have other areas. If it's outside a fire zone, it might be more difficult to answer.
So a fire, yeah, coming from the area in which the pylon once was. Would there be any difference in the flight deck effects from that scenario versus a scenario in which there was no wing fire, but the pylon had still separated?
Okay, I understand. Thank you. The only areas where we have the detection and suppression capability are in what we call fire zones. The nearest fire zone would be within the engine compartment, where we have fire detection sensors and we have suppression capability, chemical suppression capability. If you're describing something in the leading edge area of the wing, there's neither detection nor suppression capability. So there would be no intended flight deck effects that would indicate fire.
Okay, thank you for your time. That concludes my questions.
Just have a couple of follow-up questions. And this might go to Mr. Chisholm. For the DC-10, is that fuel valve in the same location as the MD-11?
Yes, the fuel valve is in the same location. The controlling mechanism was changed, as I stated.
Okay. And then is the fuel valve location, the fuel shutoff valve location, different conceptually with like a 767 or a 777 versus an MD-11?
Conceptually, I believe they operate the same, but I can't talk at what detail they're similar or dissimilar.
But location-wise, is it in the same area or is it more inboard, closer to the engine?
Fuel valves can actually be located in many different areas. Sometimes they're even on the rear spar. Sometimes they're inside the fuel tank, inside the wing. So no, they don't have to be located where this one's located.
Okay. And this is for anyone on the panel here that has knowledge on this, but what technologies are there, redundancies, for an event where a fuel valve is compromised? Anything you're aware of that you can talk to? Self-sealing lines, secondary valves?
So as I mentioned earlier, there's inherent redundancy with the engine intact.
But in the pylon separation modes, when the engine and pylon separates?
There's certainly no automatic system to shut off flow of fuel.
Thank you. Chair Hominy, that's the tech panel's questions.
Thank you. We'll move to party questions, and we'll go in reverse order, starting with UPS.
Thank you. UPS has one follow-up question from earlier. When the MD-11 fleet, or when the MD-11 airplanes were grounded, first by UPS and then the following day by the FAA, we understand that ferry flights were not permitted, even after post-accident visual inspections, because it was possible to have bearing failure and lug damage without visible race migration, all in alignment with the structures report, section 3.6. Would Boeing confirm, is that correct, or was there another reason for the denial of ferry flights?
It is a correct statement that ferry flights were not permitted. As we've discussed, the bearing, fracturing, and migration, the various states that it could be in has an impact on the stress state of those lugs. And so without understanding the stress state of the lugs, we would not be able to provide a means and substantiate a ferry flight. That's correct.
Yeah, so we could have inspected those bearings essentially every day, and it's possible that migration would not be visible on those.
I can't speculate in terms of
I think
change from
that's
day to day.
a speculative question.
I'll strike that then. No further questions.
STE San Antonio Aerospace.
No, ma'am, no questions at this time.
All right, International Brotherhood of Teamsters.
No questions.
Federal Aviation Administration.
No questions. Thank you.
Boeing.
Thank you. No questions.
One more time, UPS.
No further questions. Thank you.
No. Teamsters? Nope. FAA, Boeing, no. Okay. Board of Inquiry, Vice Chairman Graham.
Thank you, Chair. As I discussed yesterday with your colleagues, will be for the FAA on yesterday's panel. Learning from previous NTSB accident investigations and taking action to rectify identified issues is the best way to prevent similar tragedies from happening. Would you agree with that statement?
Yes.
Okay. So I want to go back and look at another one of NTSB's recommendations stemming from the 1979 DC-10 accident at O'Hare and the FAA's response to this recommendation. This was recommendation A79-98, in part asked the FAA to incorporate in type certification procedures full consideration of possible failure combinations which can result from primary structural damage in areas through which essential systems are routed. In response, the FAA stated that the complexity of the airframes and systems and rapid evolution of aircraft technology would render meaningless any attempts to specify guidance material for combined failure cases during type certification to cover all possible risks as part of their rationale to not take action to fulfill this part of the recommendation. Is this still the FAA's position today?
Yeah, I don't know that I was not familiar with that recommendation, but I think our position would be that we have a set of regulations that establish a framework for certifying aircraft. And we're deep into some of them today, considering scenarios like gear up landing, gear failure, rotor burst, things like that. And each applicant, it's their duty as an applicant to get their design approved to make sure that they integrate their structural design, their system designs, all of those things to come together. And so it's we've been focused on just a few regulations today, but there are others that are broad regulations, like 251309 is generally how we certify systems and make sure that we have where appropriate redundant designs, consideration of failures, consideration of the probability of failures or combinations of failures. And so we've got systems in place or a framework in place to certify aircraft. And once in a while, unfortunately, we have days like today where we have to go back and reassess an approved design and then make necessary changes. But the broader framework is in place.
Does the FAA today provide additional guidance regarding combined failures during type certification?
We recently issued some rulemaking around 251309 system safety analysis and 25901, which is a propulsion requirement that includes that type of guidance. So a advisory circular 251309 1B has been updated September of 2024 timeframe.
Okay. How would you provide guidance for somebody who's trying to certify to a particular part in case? Would it be through maybe an advisory circular or something for that?
Right. So for the system safety requirements, like I said, the advisory circular, that advisory circular has been updated. AC 251309, also AC 25901. So those were updated in 2024. If a new project were to come in and they are, we find that they need to step up to the latest amendment of those requirements, then we make those advisory circulars available to them and they can use that guidance.
Okay. Thank you for that. My time's up.
Member Chapman.
Thank you, Chair. Just a couple questions in this area. How similar is the MD-11 design to the DC-10 design in terms of the engine pylon design?
The MD-11 pylon design, specifically the structural attach points, the pylon forward bulkhead thrust link and pylon aft bulkhead are very similar, just minor details which we discussed earlier. The main differences would come from the engine attachments, given the difference in engine configuration.
And I think you covered this a little bit already, but were improvements made from the DC-10 design with respect to systems running through the wing near the pylon? And I think you said there were some changes made as a result of the 1979 accident. Is that right?
There were changes made that are in line with the recommendations from the 1979 accident and changes made that are in line with the recommendations from the 1989 accident, both.
The Sioux City accident?
Yes.
And for FAA, the FAA folks, are FAA's design requirements meant to prevent all engine separations, or are those requirements intended to ensure a predictable and potentially survivable outcome if there is a separation event?
The requirements are intended to ensure no separation.
And so the breakaway.
I should clarify, other than for landing events.
Right. So those breakaway requirements are specifically targeted on landing events.
Yes.
Yeah. And could we bring up exhibit 7X, figure 4? This is something Boeing developed and submitted, but it's a useful visualization for the amount of deflection that we would be talking about for the gear up landing. So for the airplane with nacelles, wing mounted engines with nacelles, and they contact the ground like that. This is the specific design case. It's a useful visualization of the design case for this model.
That's helpful. Thank you. If a wing pylon separates on an MD-11, would the crew have any way, at least in theory, obviously, probably a high workload situation, but would the crew, at least in theory, be able to stop fuel flow to the compromised engine?
So the question is for a wing pylon separation in flight.
In flight.
Yeah. So as we looked at that figure, the one looking down in the pylon area, we had the wiring for the fuel shutoff valve in that area hard mounted to the pylon. So if that pylon separated, that wiring would be compromised. So there would be no way to operate the fuel shutoff valve.
No way to shut off the fuel. Okay. Given today's engine breakaway design requirements, FAA's requirements today, would those requirements help mitigate the risk of a wing fire of the sort we saw in the UPS accident? Is there anything about today's requirements that differ in such a way that it might mitigate the risk of a wing fire like we saw in Louisville?
I would have to do an incredible amount of speculation.
And we don't want you to do that. I appreciate that. Chair, that's all I have in this area. Thanks.
Thank you, Member Chapman. Member DeLue.
Yes. So I want for clarification, I think, for the folks listening to the hearing. So when you fly a commercial jet, one of your Boeing products, and you get to the gate, do the pilots use the shutoff valve or the fire handle? Shut down the motor. If you don't know, I'll tell you. They're going to use the regular shutoff valve.
Yeah, I was thinking there's maybe a pilot in the room that could answer that.
Yeah, well, I'll answer for you. It's a shutoff valve. So I think it's important for people to know that if we had an engine fire or a failure, we use the fire handle, because when you use the fire handle, you immediately shut off fuel at the tank, off the lines. Hydraulics are shut off automatically. Electrics are shut off. You arm the agent. So there's a reason we use the fire handle. We rarely use a fire handle. In fact, I never had to use a fire handle in 37 years. So we use the shutoff valve. So there's a reason. So the design is that, just so you can clarify, the fire handle is unique because it does do a lot of things that normally would not happen when you normally shut off the engine, correct?
Correct.
And one of them is shutting off the fuel at the tank and shutting off so it immediately starves the engine of fuel.
Yeah. The two things, well, three things the fire handle can do. One is it, when you pull down the fire handle, it will shut that fire shutoff valve. It will also isolate that hydraulic system. So if it's engine one, it'll isolate hydraulic system one. And you can turn the fire valve to release suppressing agent.
Right, and it also closes, not an MD-11 pilot, but I'm almost certain it closes the bleed air valves too, because you're trying to isolate bleed air in hydraulics, correct?
I'd have to get
I can assure you it'll close the bleed air valves. So the point is the fire handle is very unique, and it has this unique function versus just shutting off an engine like you normally would at the gate. One last thing I want to emphasize on this one here, and hopefully you know, 47 years ago, there was a hearing for the DC-10 crash in Chicago. And there were a lot of safety recommendations made by board members that preceded us. And one of the recommendations was that Vice Chair Graham mentioned was about the leading edge slats that were problematic and that were one of the probable causes for the accident. So we already got that the FAA didn't really respond to it. It was a close, actually unacceptable by the NTSB. Did McDonnell Douglas / Boeing, did they comply with that safety recommendation?
Yes.
On the accident that happened in Louisville, did the leading edge slats stay extended?
So I believe the indications we see in the system's factual report are consistent with the slats staying extended. And that was the purpose of what we call the slat balance relief valves, those fuses that backstop the hydraulic pressure.
Well, they did stay extended. I agree with you. So obviously, by following the safety recommendation, the system worked.
Yes.
So we, as the NTSB, we appreciate you following those safety recommendations. That's all I have, Chairwoman Hamady.
Thank you. And I believe, Mr. Chisholm, that you referenced this earlier, but I just want to draw attention to it for folks that might be looking through the public docket. When the engine separated, the flight data recorder parameter changed to engine 1 fire. However, there's no indication on the cockpit voice recorder transcript of an oral alert. And just could you explain the system operation of the fire alerting system so people understand the data that they're looking at in the docket?
Certainly. I mentioned that when there is a fire indication, and in this case, the indication would be likely due to the simultaneous severing of the fire loop wires. So it'd be the same indication in the cockpit. What happens in the case of a fire indication is an oral warning, a display, the fire handles blink, as well as the fire shutoff valve, unless we're in the takeoff phase. So if the airplane is below 400 feet or in the first 25 seconds of flight, the oral warning and the display are inhibited by intent, because at that point, the pilot is to be focused on piloting, to be up and away, and not distracted by a non-normal. The fire handle and the fuel switch would still be illuminated, but there would be no oral, and I believe you were talking about the CVR. There'd be no indication in the CVR because it would be and apparently was inhibited.
Thank you. And also, I do agree strongly that recommendations need to be implemented. Unfortunately, we have many that are not. But one thing I do want to make sure of, just because there were a lot of media reports after the tragedy, which focused on American Airlines 191. Just the final report is in the structures group chair report in the docket, and our investigators have reviewed the accident and findings. But could you please describe the differences between the two accidents so people understand there are differences involved, Mr. Konopask?
Yes, thank you for the question. The DC-10 accident in 1979 stemmed from a maintenance-related finding that led to damage at the base of the lug. It's the same pylon aft bulkhead structure and design. However, it's at the bottom radius there where there was cracking that began, and ultimately the failure mode was similar, but it originated from a different perspective, whereas this was originating from the fatigue cracking due to the change in stress state based on the bearing failure.
Yes, but in that one, it was a maintenance error.
Correct, yes.
Okay, thank you. Member Chapman. Member Graham.
Can I just follow up on I'd like to follow up on your question. So in the maintenance area, can you explain what the difference was after that accident happened? What was the procedural change done in maintenance so that would not happen again?
Yes, I'm going to speak at a high level based to the best of my knowledge.
You bet.
The procedure for removal and installation of the pylon was being performed with the engine installed, using additional equipment to move the entire both parts together. And so installing the pylon on the wing presents it is a very detailed task that requires a lot of precision. And so that's where the adverse damage came from. And so this is where the procedures, to the best of my understanding, were updated such that it specified you're not allowed to do that anymore and had to treat them independently. So removal of the engine first and then removal of the pylon. And then on the reinstallation side, you install the pylon first and then the engine.
You bet. Yeah, thanks for the clarification. I just want people to know that there was a safety recommendation, and that was one of the changes, is that pylon, and then you attach the engine, as opposed to one solid time.
Yes.
Thank you.
All right, any more questions from the Board of Inquiry? All right, back to technical panel.
Thank you, Chairwoman. I have a few follow-up questions. I want to talk a little bit about FAR Part 25-1309 that addresses system safety analysis. How was it determined which systems apply and which systems need to be considered for that requirement?
Yeah, it's all systems. It's how we certify systems is typically through 1309. There are a few regulations that have carve-outs, like for flight controls, 25671 is an explicit consideration of a system, and also 25901 with regard to the rotor burst scenario ties into that. So it's tied into a few other, it's a little more complicated than that, but yeah, 1309 would be used for certifying systems.
So does 1309 apply to systems routed through or near pylons? Does it require that they be protected then from pylon separation?
No, not necessarily. The 1309 would require assessment of system failures, single failures and multiple failures, combinations of failures, but not particular threat scenarios like the gear up landing. That's in the normal airplane design, the pylon should never be separated, and it would only be separated in very specific cases. And in those times, Boeing discussed that they demonstrated for the gear up landing with that, as was shown, that small amount of deflection of the engine in the upward direction, that the system continued to perform its intended function of being able to shut off the fuel shutoff valves.
I guess I'm just trying to understand when 571 takes over and when 1309 is applicable. Maybe, Mr. Martin, maybe you can speak to that.
Yeah, we would say that this demonstration that complete engine mount failure is extremely improbable is substantiated through compliance with the design strength requirements and fatigue and damage tolerance requirements. So through those strength and fatigue requirements, we ensure that failure of the pylon, complete separation of the engine will not occur.
So it really comes down to the probability of this scenario happening. Is that correct?
Except that we don't really use probability in that, at least not like other systems for the structures evaluation. But yes.
Would it be fair to say the design approval, the original design and the AWL are intended to never have a structural failure?
Okay, thank you. Those are my questions.
Chair, how many? That's the tech panel's questions.
Great, any additional party questions? Hearing none. Okay, and nothing from the board. All right. You're good? So that concludes our investigative hearing. On behalf of my fellow board members and the NTSB staff, we extend our appreciation to the witnesses for their testimony and the parties certainly for your cooperation, not only at this hearing, but since this tragedy occurred. Mr. Johnson, can you review any new exhibits that were admitted during this hearing?
Yes, ma'am.
Oh, I have to read his. Oh, hold on. Oh, photos of the exemplar. We have to work on handwriting. Photos of the exemplar bulkhead. Is that it? We have a lot of other get backs, but those aren't part of the exhibits, but we'll make sure to, that we put together a list and send it to you. And if it's okay with Mr. Shin, those would be due back at the same time of the initial submissions from the parties to the investigation, which are due on June 19th.
Yes, and I'll make one statement for the parties. If you are going to make a party submission, send that to me. I will collect all party submissions and then send it out to the other parties as well. So don't copy the other party spokespersons, just send it to me. I'll send the party submissions out as a single batch to everyone.
Is everyone clear on that? Yep. Okay. The record will remain open for the addition of that exhibit admitted during the hearing. The transcript of these proceedings will be available to the parties and witnesses electronically within 7 days of the completion of the hearing. Any corrections to that transcript must be sent to Mr. Shin, the hearing officer, by June 19th, 2026. The transcript of the hearing and all materials entered into the record will become part of the public docket. I'd like to extend the board's gratitude to our colleagues across the agency, starting with Mr. Shin and the entire investigative team. Thank you all so much. You all did an excellent job, and you did so under very challenging circumstances. The accident occurred during one of the longest government shutdowns in history, or the longest. Despite having worked for weeks without pay and the support of our furloughed colleagues, you nevertheless stepped up to carry out our vital safety mission, launching to the scene of this devastating event to document, collect, and preserve perishable evidence. Once the shutdown ended, you all continued to work nights and weekends to ensure that the investigation, including this hearing, remained on track. And we have your perseverance and resilience to thank for that. Thank you. Over the last 2 days, also, your deep expertise and technical rigor were on full public display, as was your unwavering commitment to the principles of independence and objectivity. In other words, you once again helped demonstrate why the NTSB maintains a reputation as the world's leading accident investigation agency. So thank you for your dedication. And I know not everyone is up here that participated, but thank you all. The board also extends its deep appreciation to our colleagues in the following offices for their support of this hearing: the Office of Aviation Safety, the Office of the Chief Financial Officer, Office of the Chief Information Officer, Office of the General Counsel, Office of the Managing Director, Office of Research and Engineering, Office of Safety Recommendations and Communications, and of course the offices of Vice Chairman Graham, Members Chapman and DeLu, as well as my team. I'd also like to thank the following staff for their work on various logistics associated with hosting the event in our boardroom: Mr. James Anderson, Mr. Chris Bueland, Mr. Chris Blumberg, Mr. Teddy Brown, Ms. Deidre Esters, and Mr. Carl Perkins. In the past 2 days, we've shed important light on the facts and circumstances of the November 4th, 2025 tragedy involving UPS Flight 2976, all of which we'll consider in our final report. Before I close, I want to ensure the public knows what to expect from the NTSB going forward, especially the survivors and those who lost loved ones in this tragedy. We are still in the fact-finding phase of this investigation. The hearing, of course, will spur additional questions, and we'll need to collect additional documents and get additional questions answered. That could also mean additional interviews. And then we'll have to take that time to look through all those documents to make sure that we don't need or get additional documents that we need to get from those documents. That does take time. I know that's difficult to hear, but it takes time to get to the right answer, not the fast one. We want to make sure that we do a quality investigation and get to the right facts, so that we can get to the right solutions and the right recommendations. So we appreciate your patience. Once the fact-finding phase of our investigation is concluded, we'll move on to the analytical phase where our staff exerts its full independence and works through the analysis part of the investigation, as well as the draft findings, probable cause, and safety recommendations. At the conclusion of that, once we have a draft final investigative report, we will have a public board meeting. Those proceedings, like I said, are public, and you can see not just how we're investigating this accident, but who is doing the work with a full complement of our staff at that board meeting. So with that, I am going to close and just once again thank the entire investigative team, the Board of Inquiry, staff, and I also want to thank the parties and the witnesses. Truly, it was a very informative couple of days, and really appreciate your patience, your answering all of our questions, and providing of the information we need to conduct our investigation. And that concludes our hearing. We stand adjourned.